Our universe, as we know it, can be traced back to a singular, momentous event, the Big Bang. But what then lies beyond that defining threshold? What occurred before time and space, as we understand them, came into existence? From the mysterious realm of quantum mechanics to the expansive concept of cosmic inflation, we will delve into the cutting-edge theories that strive to answer these questions. We will explore ideas that attempt to pierce the veil of what preceded the birth of our universe, challenge the very meaning of nothingness itself, and contemplate the bold possibility of a multiverse. The idea of nothing, true nothing, has captivated the imaginations of philosophers and scientists for centuries. In the realm of science, though, nothing is far from a simple concept. It refers not merely to an absence, but to the complete absence of matter, energy, and even space itself. Yet, there's an essential distinction to be made between nothing and the void. A vacuum, often mistakenly thought to be the epitome of emptiness, still holds the potential for energy. Even in this seeming nothingness, there can be fluctuations, brief bursts of virtual particles that blink into existence and vanish just as quickly. Quantum mechanics reveals a surprising truth. The vacuum state, far from being empty, is a dynamic field in constant fluctuation. It's as though the very fabric of space is alive, bubbling with possibilities. In this realm, particles appear and disappear at the quantum level in a never-ending dance of potentiality. What we once thought of as a barren void is actually teeming with life, just beyond the reach of our perceptions. This understanding shatters our classical notions of what nothingness really means. It forces us to reconsider the very foundation of the universe itself. What if this quantum activity, this fundamental unpredictability, is the key to unlocking some of the deepest mysteries of existence? As our grasp on the nature of the cosmos evolves, these discoveries, once thought to be merely theoretical, are beginning to reshape our understanding of reality, from the tiniest quantum fluctuations to the grandest scales of the cosmos. The implications are staggering. Could our universe have emerged from this quantum soup of possibilities? Might there be other realms beyond our own, each with its own set of laws and possibilities, forming a vast multiverse? As we venture further into the unknown, we must ask, could this intricate, fluctuating sea of potentiality be a window into what existed before our universe came into being? Furthermore, when cosmologists explore the origins of the universe, they encounter the mind-boggling concept of nothingness in the context of the Big Bang. Before this monumental event, neither space nor time, as we understand them, existed. The idea of this before is profoundly unfathomable. What came before the Big Bang is a question that pushes the limits of human comprehension. The transition from absolute nothingness to the birth of everything we know is a dramatic shift in the fabric of reality itself. While nothingness might appear simple at first glance, from a scientific perspective, it reveals an intricate dance between absence and untapped potential. This understanding of the universe's origins has profound consequences, inviting us to reconsider what we know about existence. It compels us to ask questions not just about how the universe began, but about the very foundations of reality. In this way, nothing can lead to something utterly unimaginable. Physicists approach the concept of absolute nothingness as a state that lacks not just matter and energy, but space and time themselves. To wrap our minds around this is no small feat. Our entire experience and understanding of existence are built on things that are tangible, measurable, and observable. Thus, scientists often turn to philosophical inquiry to help make sense of such an elusive concept, blending it with advancements in theoretical physics. Absolute nothingness is often compared to the vacuum of space, a state that, while devoid of matter, is far from empty. In fact, a vacuum is teeming with fluctuating quantum fields that give rise to virtual particles, which appear and vanish in the blink of an eye. In contrast, true nothingness, as theorized by physicists, would be a state completely devoid of even these ephemeral phenomena. This sharp distinction between a vacuum and nothingness forces us to confront the boundaries of existence. What does it even mean to exist if not a state of constant energy and matter? How do we define existence in models like the Big Bang Theory, where the entire universe seemingly erupted from nothing? This brings us to a challenging yet fascinating question. What existed before the Big Bang? If absolute nothingness is the backdrop, then it implies a condition that is both timeless and formless. Without space and time, there would be no framework to which the laws of physics could apply. It raises profound questions about causality and the very nature of beginnings. How can something emerge from nothing? How can the universe, as we know it, begin from a state where physics has no hold? As researchers venture deeper into the mysteries of the cosmos, they are finding that conceptualizing true nothingness is not just a metaphysical puzzle, but a central challenge in understanding the nature of the universe itself. This question shapes much of contemporary scientific inquiry. It beckons scientists to explore fields like quantum mechanics, string theory, and beyond, domains that may ultimately provide clues to the universe's very existence. The search for answers doesn't merely promise to reshape our understanding of the cosmos, but may uncover the very reasons why the universe is here, why it exists in the first place. The debate surrounding whether true nothingness can even exist is not confined to scientists alone. Philosophers, too, grapple with the implications. From a physical standpoint, the idea of nothingness, defined as the absence of matter, energy, space, and time, poses significant challenges. In practice, there seems to be no space within our observable universe that is completely void of physical properties. Even in the deepest, most profound vacuum of space, quantum fluctuations persist, creating virtual particles that flicker in and out of existence. This phenomenon illustrates a critical point. Space is far from empty. It is filled with a sea of potential energy, constantly teeming with the possibility of new particles, waves, and fields. In light of this true nothingness, where no matter energy, space, or time exists, cannot coexist with the principles of physics that govern our universe. The search for a true void has yet to yield any region of space completely devoid of physical properties. This elusive concept of absolute nothingness continues to challenge not only our scientific understanding, but the very way we think about the universe and our place within it. When we delve into the origins of our universe through the lens of the Big Bang, we are confronted with fundamental questions about what may have existed before this monumental event. Theories suggest that the universe emerged from a state of extremely high density and energy, yet they fail to provide a clear explanation of what, if anything, preceded this cataclysmic moment. Did the universe spring from nothing, or was there something before it? Something beyond our current grasp of understanding? This question reaches deep into the realm of philosophy, challenging our perception of existence itself. Can something truly come from nothing? And if so, what does nothing even mean? The concept of pure nothingness, as we ponder it, seems elusive and abstract. It stands in stark contrast to the tangible reality that science works to explain. While intriguing, the notion of true nothingness remains largely theoretical within the framework of contemporary scientific understanding. However, the search for answers stirs our imagination and forces us to confront the boundaries of our knowledge. The questions raised compel us to reconsider the very fabric of reality, urging us to explore whether there is more to existence than what we experience in our everyday lives. Still, in the vast cosmos we observe true nothingness, an absolute void, does not appear to exist. Instead, what we find is the concept of the quantum vacuum, a curious and highly intriguing state in the realms of quantum physics. At first glance, one might assume the quantum vacuum is an empty void. After all, the word vacuum suggests emptiness. However, this is far from the truth. In reality, the quantum vacuum is anything but empty. It is a dynamic and rich environment, teeming with potential. Even in the absence of particles, it is alive with quantum fields that fill the very fabric of space. What makes the quantum vacuum so fascinating is its complexity. Though it is considered the lowest possible energy state of a quantum field, it is far from a still or quiet backdrop. Instead, it is filled with fluctuating energy. Virtual particles spontaneously pop in and out of existence, influenced by the underlying energy fields that ripple through space. These fleeting particles arise from the quantum fluctuations in the vacuum and vanish just as quickly, highlighting the transient and volatile nature of this state. This leads to a critical distinction. The quantum vacuum is not the same as nothingness. While true nothingness implies the absence of everything, matter, energy, and even the space through which they exist, The quantum vacuum exists in a state brimming with fluctuating energy. It is a wellspring of potential, a source of unseen forces that shape the very nature of our universe. Quantum mechanics demonstrates that this vacuum state has real, observable consequences. One such phenomenon is the Casimir effect, in which two closely spaced plates in what seems to be empty space experience an attractive force. This force arises from the fluctuations in the quantum vacuum, fluctuations that we cannot see but that have tangible effects. Such discoveries force us to reconsider our assumptions about empty space. What was once thought of as an inert void is in fact an active and vibrant stage for the theater of the universe. The quantum vacuum's activity extends beyond the creation of virtual particles. It participates in the universe's behavior, driving the interactions between particles. These interactions, such as particle-antiparticle creation and annihilation, demonstrate the interconnectedness of all things in the cosmos. In this sense, the quantum vacuum is not merely a background against which particles move. It is a player in the ongoing drama of existence, shaping the structure of the universe itself. Ultimately, the quantum vacuum challenges our classical notion of what a vacuum should be. It forces us to confront the idea that emptiness may never be as simple as it seems. Even in the absence of visible matter, the quantum vacuum holds an intricate web of interactions and energy, reshaping our understanding of what is truly empty. It offers a glimpse into the profound dynamics that govern reality at the most fundamental level, a level where the boundary between something and nothing becomes increasingly difficult to define. At the core of all these explorations lies the concept of zero, a concept that is fundamental to our understanding of nothingness. In mathematics and physics, zero serves as the placeholder for the absence of quantity. It is an essential tool, a cornerstone upon which much of modern science is built. Yet even zero is not as simple as it appears. In the quantum realm, where the very fabric of space-time is in constant flux, zero may be more than just a numerical abstraction. It may be a gateway to deeper truths about the nature of the universe itself, a reminder that nothingness, far from being an empty void, is an idea that continues to evolve and elude our understanding. Through the lens of quantum physics, nothingness is not an absence, but a field of infinite possibility. The quantum vacuum reminds us that reality, in its most fundamental form, is far more intricate and interconnected than we could ever have imagined. What we once thought of as empty space is anything but. It's a dynamic, ever-changing environment full of potential, energy, and life, continually shaping the universe as we know it. And as we continue to study it, we are left with the realization that the true nature of nothingness may be far more complex than we ever thought possible. However, when examined in the context of physical reality, the concept of zero takes on layers of complexity, especially in relation to the vast, invisible forces that govern the universe, such as space, energy, and quantum fields. Zero is not just a placeholder or an abstract number in physics. It is a reference point that allows scientists to articulate the absence of measurable quantities within the framework of established physical laws. For example, zero electric charge or zero temperature represents states where specific properties simply do not exist. In this sense, zero acts as a way to quantify absence, offering a tool to understand how things might be missing within a defined context. This interpretation of zero sharply contrasts with the concept of nothingness, which suggests a state devoid of any measurable parameters. Nothingness implies an utter void, an absence of not just matter, but structure itself. Zero, on the other hand, has a more nuanced role. It does not denote a complete vacuum or emptiness. Rather, it serves as a starting point for understanding the energy and dynamics of the universe. It allows for the exploration of how energy fluctuates and particles behave even in seemingly empty space. In modern physics, particularly quantum mechanics, the relationship between zero and nothingness becomes even more intricate. The vacuum state, often referred to as empty space, is not truly devoid of activity. While it is described as having zero particles, the vacuum is far from inert. Instead, it is an active energy field where minute fluctuations are constantly occurring. Here, zero does not signify a complete lack of physical properties. Rather, it marks a baseline from which variations in energy, particle dynamics, and forces can emerge. This complexity helps scientists probe the very fabric of reality, showing that even in a zero state, the universe is anything but empty. Moreover, in the field of cosmology, zero finds additional significance through the concept of a zero-energy universe. Some theories propose that the universe could have originated from a state of perfect equilibrium, where the total amount of matter and energy sums to zero. In this scenario, the cosmos might have emerged from a void, not in the sense of an absolute nothingness, but from a perfectly balanced condition of energy and matter. This idea suggests that the transition from a physical void to a universe filled with galaxies, stars, and particles could occur without requiring a pre-existing state of nothingness. Zero, then, becomes a bridge, a link that allows physicists to explore the interplay between absence and presence, the void and the cosmos. In the realm of quantum field theory, the notion of nothingness takes on an even more profound and active role. Here, nothingness is not an empty void, but is conceptualized as the vacuum state filled with fluctuating quantum fields. These fields are not mere abstractions. They represent the fundamental forces and particles of the universe, and their behavior provides insights into how particles interact and how the universe operates at the most fundamental level. The vacuum state in quantum field theory is far from being devoid of activity. Instead, it is alive with the creation and annihilation of virtual particles, which emerge and vanish continuously due to fluctuations in vacuum energy. These virtual particles, though imperceptible to our everyday senses, influence the observable world in surprising ways. For instance, the phenomenon known as the Casimir effect demonstrates how vacuum fluctuations can lead to physical forces. In this case, two uncharged plates placed very close together in a vacuum will experience a force that causes them to attract each other. This is a direct result of the quantum fluctuations occurring in the vacuum, showing that even empty space has properties that can influence the physical world. Furthermore, the concept of nothingness in quantum theory is deeply connected to the stability and symmetry of the universe. In particle physics, the stability of the universe is often defined by the energy states a system can occupy. The vacuum state represents the lowest possible energy level, serving as a baseline against which all other energy states are measured. When particles interact, they can transition between different energy levels, often involving the creation or annihilation of virtual particles. This entire process occurs within the vacuum itself, in a realm that seems empty, yet is constantly in flux. Thus, the idea of zero and nothingness in physics serves not as a simple negation of existence, but as a gateway to understanding the very nature of reality. Far from being devoid of structure or activity, the vacuum and its associated quantum fields are central to the functioning of the universe. What we once thought of as emptiness is now seen as an active, dynamic stage on which the forces and particles of the universe play out their roles. Nothingness challenges our classical intuitions about reality in profound and unexpected ways. At first glance, the concept of nothing seems straightforward, an absence, a void. Yet in the world of quantum mechanics, nothingness is anything but empty. The very presence of the vacuum state, often considered the purest form of emptiness, reveals a dynamic environment brimming with potential. This idea forces us to reconsider what we perceive as empty space, and prompts us to ask deeper questions about the origins of particles and even the universe itself. Nothingness, it turns out, is not merely a philosophical abstraction, but a crucial element in understanding the complex, often paradoxical nature of the universe. Across cultures and religions, the concept of nothingness has been understood in varying, often contrasting ways, each reflecting deep philosophical insights about existence, reality, and the nature of the cosmos. In Western thought, particularly in the tradition of ancient Greece, nothingness has been regarded with suspicion. It was often associated with chaos, void, and the absence of being. The philosopher Parmenides famously argued that nothing comes from nothing, laying the groundwork for future metaphysical debates that would define much of Western philosophy. For Parmenides, nothingness was a denial of existence itself, something to be avoided. In stark contrast, Eastern philosophies have often embraced the idea of nothingness, albeit in very different ways. Buddhism, for example, presents nothingness as a form of ultimate reality, encapsulated in the concept of shunyata, or emptiness. In this view, all phenomena are seen as devoid of inherent essence, and attachment to fixed notions of existence and non-existence is the root of suffering. Through awareness of this emptiness, Buddhists believe one can transcend personal desire and attachment, ultimately attaining enlightenment. This understanding of nothingness emphasizes the interconnectedness of all things, a core tenet of Buddhist thought that encourages harmony and liberation from the cycle of suffering. Similarly, Taoism also reveres the concept of nothingness, though its approach differs in tone and context. In the Tao Te Ching, the Tao, the Way, is described as the fundamental principle that flows through all things. This Tao is not simply the absence of something, but is itself an active force that allows creation to unfold. In Taoism, nothingness is a fertile ground, a space of infinite potential from which all existence emanates. It is not a void to be feared, but rather a vital force that enables balance and harmony in the universe. Indigenous cultures around the world have often understood nothingness as something both powerful and transformative. Many creation myths, for example, describe a primordial state of chaos or emptiness as the source from which the universe emerges. In these traditions, nothingness is not merely an absence, it is a space where transformation and creation take place. Here, the void is seen as an essential part of life's cyclical nature, a symbol of renewal and interconnectedness. Despite its different cultural interpretations, nothingness remains a concept that is both elusive and powerful, one that continues to shape existential, philosophical, and scientific inquiries worldwide. The challenge of understanding absolute nothingness lies in its very nature. It exists outside the boundaries of our lived experience. Our lives are filled with objects, energy, and relationships, and thus we struggle to imagine a state that lacks not only substance, but also space and time. The very fabric of human thought is tied to ideas of something, making it difficult to truly conceptualize a state devoid of everything. For centuries, philosophers have grappled with this concept. In existential philosophy, nothingness is often framed as the absence of essence. Jean-Paul Sartre, for instance, argued that it is through our awareness of nothingness that we come to understand our freedom and the ability to create meaning in our lives. Nothingness, in this sense, is not just a void. It is a space that makes possible the creation of identity and purpose. But while the idea of nothingness can be articulated, its full comprehension remains elusive. In the realm of science, particularly in theoretical physics, the concept of nothingness becomes even more perplexing. The absence of matter, energy, space, and time challenges human intuition. Take, for example, the vacuum of space, which in classical terms might be thought of as an empty void. But in quantum theory, even this empty space is teeming with quantum fluctuations, particles appearing and disappearing at random. Far from being nothing, it is a landscape full of potential, a state of constant activity. This discovery underscores the limits of human understanding. Our very conceptions of reality, grounded as they are in substance, interaction, and continuity, do not easily extend to this strange, fluctuating nothingness. Thus, while humans may engage conceptually with the idea of nothingness, truly grasping its nature is nearly impossible. Our experience as beings who interact with a world full of matter and energy makes the true understanding of absolute nothingness almost unattainable. Yet this very challenge sparks rich dialogues in both philosophy and science, pushing the boundaries of our understanding of existence in the cosmos. The psychological impact of contemplating nothingness varies widely depending on individual beliefs and life experiences. For some, the very idea of nothingness can evoke feelings of existential dread or anxiety. The realization that all experiences, relationships, and achievements might ultimately be transient can be overwhelming. This void or absence seems to strip away the meaning from life, forcing individuals to confront their own mortality and sense of purpose. The unknown expanse of nothingness can feel like an abyss, prompting deep questions about identity and the significance of human existence in the vastness of the universe. Conversely, others find freedom and liberation in contemplating nothingness. This perspective often emerges from philosophical traditions such as Buddhism, where emptiness is seen not as a threat, but as an opportunity for profound peace. By letting go of attachment to fixed notions of existence and non-existence, individuals can free themselves from suffering and find clarity. Recognizing the impermanence of all things, these traditions teach allows individuals to live more authentically, with greater awareness of the interconnectedness of all life. In therapeutic settings, grappling with the concept of nothingness can offer opportunities for personal growth and reflection. Discussions of existential concerns often prompt individuals to confront their deepest fears and examine their values and aspirations. By engaging with nothingness in a safe, structured environment, people can gain insights into their lives and develop resilience in the face of uncertainty. This process of exploration, paradoxically, can lead to greater self-understanding and empowerment as individuals navigate the vast unknown of existence with a renewed sense of purpose and clarity. Existential exploration has long been a gateway to understanding the complexities of human existence. However, it also offers something more profound: connection. The shared uncertainty of our place in the universe can create bonds between individuals, forming communities that navigate these deep, often unsettling questions together. In facing the void, people find solace in one another, fostering solidarity and mutual understanding. As they journey through the ambiguity of nothingness, they find their relationships enriched, their experiences deepened, and their search for meaning given new context. While the contemplation of nothingness can, at times, stir feelings of discomfort and anxiety, it can also lead to personal growth, transformative discoveries, and a profound understanding of life itself. The concept has profoundly influenced both art and literature, becoming a rich source of exploration for creators throughout history. In many works, the theme of nothingness serves as a backdrop against which the struggles and triumphs of human existence are framed. Artists and writers have delved into this concept to express feelings of alienation, despair, or even liberation, reflecting the turbulent, chaotic, and often uncertain nature of the universe. In literature, the presence of nothingness is especially evident in existential works. Authors like Franz Kafka and Samuel Beckett have grappled with this theme, crafting narratives that expose the absurdity of life. Kafka's stories often center around characters ensnared in bureaucratic, meaningless systems, evoking a deep sense of existential dread. These characters, trapped in the void of pointless struggles, reflect the grim reality of human life in a seemingly indifferent world. Similarly, Beckett's play Waiting for Godot embodies the essence of nothingness. The two characters engage in repetitive, seemingly pointless conversations as they wait for an event, Godot, that may never come. The play forces audiences to confront the silence of existence, leaving them with the unsettling realization that meaning may be elusive and perhaps even unattainable. In the world of art, the concept of nothingness has been explored through various movements, most notably minimalism and abstraction. Artists like Kazimir Malevich and Yves Klein sought to distill their works down to their most essential forms, often embracing emptiness as a central theme. Malevich's iconic black square is a prime example of this exploration. The painting itself, stark and empty, invites the viewer into a meditative space, a place to contemplate the void. It is not just a lack of content, but an invitation to consider the absence, the space in which all things exist and from which they emerge. Similarly, Yves Klein's monochromatic blue works challenge viewers to reflect on the nature of existence beyond the material world. Klein sought to evoke a transcendence of physical form, allowing the color to become a symbol of the infinite, of nothingness itself. Through this minimalism, these artists encourage a deeper emotional and intellectual engagement, urging viewers to consider the relationship between presence and absence. The exploration of nothingness also inspires innovation within the realms of both art and literature. By abandoning traditional forms, structures, and recognizable narratives, creators challenge their audiences to engage more intimately with the work. The absence of familiar patterns creates a void that viewers and readers are compelled to fill with their own interpretations, often leading to a more personal, reflective experience. This embrace of nothingness opens new possibilities for creative expression, allowing for the exploration of themes like identity, reality, and the human condition in ways that are both challenging and enriching. Ultimately, the concept of nothingness sparks profound philosophical discussions, inviting artists, writers, and thinkers to probe the depths of existence itself. It offers an opportunity to question reality, to confront the void, and to find meaning in the spaces between what is and what isn't. In doing so, it brings us closer to understanding our place in an ever-expanding, ever-changing universe. The Big Bang Theory, which remains the dominant explanation for the origin of the universe, provides a fascinating lens through which to view this philosophical exploration. Around 13.8 billion years ago, the universe began as a singularity, an incredibly hot, dense point, before it expanded into the vastness of space as we know it today. This expansion not only marks the beginning of time and space, but also opens up a profound inquiry into the nature of nothingness. The universe, born from a state of nothingness, continues to expand into the unknown, raising questions about the very origins of existence and what lies beyond the observable universe. As the universe expanded, it began to cool, allowing energy to transform into subatomic particles. Over time, these particles combined, eventually giving rise to the formation of atoms, stars, and galaxies. This process, as fundamental as it is, was first extensively explored in the early 20th century, with many pivotal contributions from key scientists. The concept of an expanding universe was first proposed by Georges Lemaitre, a Belgian priest and physicist around the 1920s. He introduced the idea that the universe had begun from what he called a primeval atom, which exploded into existence. Lemaitre's groundbreaking theory laid the foundation for what would later evolve into the Big Bang Theory. His work ignited a new era of cosmic exploration, offering a radical shift in our understanding of the universe's origins. This initial idea was further developed by Edwin Hubble in the late 1920s. Hubble's observations led to one of the most important breakthroughs in cosmology. Galaxies, he discovered, were receding from us. His work showed that the farther a galaxy is, the faster it moves away from us. This relationship became known as Hubble's law, offering solid observational evidence for an expanding universe. It provided the empirical support Lemaitre's theory needed, showing that the universe was not static but continuously stretching outward, just as the Big Bang Theory suggested. The 1940s brought additional confirmation for the Big Bang Theory with the discovery of cosmic microwave background, CMB, radiation. This faint afterglow, still detectable today, represents the residual heat left over from the early universe. It is a relic from the time when the universe was a hot, dense soup of particles. The discovery of this radiation by Arno Penzias and Robert Wilson in 1965 marked a pivotal moment in cosmology, providing direct evidence of the universe's birth and its dramatic initial conditions. This expanding universe model continued to gain momentum as more evidence stacked up. One of the most compelling pieces of support comes from the CMB itself. The uniformity of this radiation across the sky reveals a critical feature of the early universe. It suggests that just after the Big Bang, the universe was incredibly hot and dense, slowly cooling over billions of years to form the cosmos we observe today. The temperature fluctuations in the CMB radiation also offer clues about the distribution of matter in the early universe, further confirming predictions made by the Big Bang model. Another line of evidence comes from the redshift observed in distant galaxies. As Hubble's law suggested, galaxies farther from us are receding more quickly, a phenomenon that implies a past where the universe was far more concentrated. This observation strengthens the idea that all matter in the universe was once confined to a small, incredibly dense point, aligning perfectly with the Big Bang model. The consistent correlation between distance and redshift serves as powerful proof that the universe is indeed expanding. In addition to these findings, the relative abundance of light elements, hydrogen, helium, and lithium, provides further confirmation of the Big Bang. These elements were formed in the first few minutes after the explosion, during what is known as Big Bang nucleosynthesis. The proportions of these light elements in the universe match precisely with what theoretical calculations predict, reinforcing the idea that the universe began in an extremely hot and dense state. Furthermore, the large-scale structure of the universe, with galaxies forming clusters and massive cosmic filaments stretching across the void, offers another compelling piece of evidence. These vast cosmic structures align with predictions made by the Big Bang Theory about the universe's evolution over billions of years. The influence of dark matter, an unseen but critical force in shaping these structures, is also consistent with the model's expectations, offering additional corroboration. Together, these diverse lines of evidence form a robust and cohesive framework that has solidified the Big Bang Theory as the leading explanation for the origin of the universe. It has transformed our understanding of cosmic history, giving us a picture of a universe that began from a single, incredibly dense point and has since evolved into the vast, complex structure we observe today. To date the occurrence of the Big Bang, scientists use a variety of techniques to study the universe's present state and its evolutionary history. One of the primary methods involves analyzing the cosmic microwave background radiation, which provides a snapshot of the universe when it was roughly 380,000 years old. At this point, the universe had cooled enough for electrons and protons to combine and form neutral hydrogen. By examining the tiny temperature fluctuations in the CMB, scientists can calculate the expansion rate of the universe and estimate how much time has passed since the Big Bang. Another important tool for dating the Big Bang comes from studying the rate of expansion itself. Hubble's law allows astronomers to measure the redshift of distant galaxies, determining how fast they are moving away from us. This expansion rate, known as the Hubble constant, can be combined with models of cosmic evolution to estimate the universe's age. Current measurements place this age at approximately 13.8 billion years, a timeline that continues to refine our understanding of the universe's vast history. Together, these methods provide a detailed and ever-deepening understanding of the universe's origins and age, securing the Big Bang Theory as the prevailing model of the cosmos. Scientists have long turned to the universe's oldest celestial objects for clues about its age. One of the most significant examples of this is globular clusters. These are dense collections of ancient stars, some of which have been around for nearly 13 billion years. By studying these clusters and applying models of stellar evolution, scientists can establish a lower limit on the age of the universe. Observations have shown that some of these clusters are nearly as old as the universe itself, which confirms that the Big Bang must have occurred well before they formed. Alongside this, the study of light elements, particularly hydrogen and helium, provides additional insight. These elements, as predicted by the theory of Big Bang nucleosynthesis, are present in the proportions we observe today because of specific conditions in the early universe. The abundances of these elements serve as a cosmic fingerprint, offering a timestamp for when the Big Bang occurred and further refining our understanding of the universe's age. Combined, these methods form a comprehensive approach to uncovering the timeline of the Big Bang and the subsequent evolution of the universe, collectively reinforcing the notion that the universe is roughly 13.8 billion years old. One of the most critical pieces of evidence for the Big Bang theory is the cosmic microwave background, CMB, radiation. This faint radiation permeates the entire universe and originates from a time when the universe was still in its infancy. Roughly 380,000 years after the Big Bang, as the universe cooled, electrons and protons combined to form neutral hydrogen atoms. This allowed photons, light particles, to travel freely for the first time, making the universe transparent and marking a key moment in its evolution. The CMB now has a nearly uniform temperature of about 2.7 degrees Kelvin, but it contains slight fluctuations known as anisotropies, which are crucial. These tiny variations hold the key to understanding the distribution and density of matter in the early universe. By analyzing these fluctuations, scientists can gain valuable insights into the universe's initial conditions, its rate of expansion, and how structures like galaxies and clusters began to form over billions of years. The significance of the CMB goes beyond simply supporting the Big Bang theory. Through its study, scientists have been able to refine cosmological models, investigate the elusive nature of dark matter and dark energy, and probe the fundamental forces that govern the universe. Missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have provided precise measurements of the CMB, offering critical data on the age, composition, and evolution of the universe. The CMB also provides a snapshot of the conditions that existed just after the Big Bang, allowing scientists to explore the early universe's inflationary period. a theory that suggests the universe underwent rapid expansion in its earliest moments, a process that ultimately led to the large-scale structures we observe today. In this sense, the CMB serves not only as a relic of the universe's origins, but also as a vital tool for understanding the very fabric of the cosmos, influencing both theoretical and observational cosmology. The Big Bang Theory itself presents an awe-inspiring narrative of the universe's birth and evolution. According to this theory, the universe began as an infinitesimally small, dense point around 13.8 billion years ago. From this singularity, a monumental explosion occurred, marking the birth of space, time, and all the matter that would eventually fill the cosmos. As this initial explosion unfolded, the universe began expanding at an astonishing rate, a phenomenon that continues to this day. In the immediate aftermath of the Big Bang, the universe was incredibly hot and dense, but as it expanded, it began to cool, allowing particles to form. This cooling process led to the creation of the first simple atomic structures, primarily hydrogen and helium, which clumped together under the force of gravity to form stars and galaxies. The spacing between these galaxies is directly linked to the ongoing expansion, a process that has continued uninterrupted since the universe's explosive beginning. This expansion is not only evident in the increasing distances between galaxies, it also reshapes the very fabric of space-time itself. A crucial discovery in the 20th century was that galaxies are moving away from one another. This phenomenon, often summarized by the term redshift, describes how light from distant galaxies shifts toward the red end of the spectrum as they recede from us. The further a galaxy is, the faster it appears to be moving away. This relationship is encapsulated by Hubble's law, which indicates that the universe has been expanding ever since that initial explosion. Observations now suggest that 13 or so billion years after the Big Bang, the universe is still growing. More intriguingly, recent research has revealed that the universe's expansion is accelerating. This mysterious acceleration is attributed to a force known as dark energy, which constitutes a significant portion of the universe. However, the true nature of dark energy remains one of the greatest unsolved puzzles in cosmology. Despite this, its presence and influence are undeniable as it continues to shape the universe's expansion at an ever-accelerating rate. The universe we witness today, vast and awe-inspiring, owes its existence to a sequence of dramatic events that began in the first moments after the Big Bang. In fact, the universe's ongoing expansion, coupled with the mysterious influence of dark energy, suggests a continually evolving cosmos, one that reshapes our understanding of its future and the fundamental forces that govern it. The first seconds following the Big Bang remain beyond our true grasp, a period unlike any other in the universe's existence. Within those initial microseconds, the universe was a furnace, an incredibly hot, dense sea of energy and fundamental particles. Temperatures soared to billions of degrees, and the basic forces of nature, such as electromagnetism and gravity, were unified into a single state. The conditions during this time were unfathomable by modern standards, with the very fabric of matter and energy profoundly different from anything we can comprehend today. As the universe began its dramatic expansion, it entered what is known as the Planck epoch. This phase, which lasted just 1,000th of a second, was marked by rapid inflation, a sudden exponential stretching of space-time. This event not only smoothed out irregularities, but also set the stage for the universe's large-scale structure. As the cosmos continued to cool, the once unified forces began to separate. The universe, still chaotic and in flux, witnessed the birth of particles like quarks, electrons, and neutrinos. However, these particles were not destined to last long. In a matter of moments, they annihilated one another in a violent dance, leaving behind only a small fraction of their original numbers. Around 1 second after the Big Bang, temperatures had cooled enough to allow quarks to bind together, forming protons and neutrons. This milestone was essential for the formation of atomic nuclei in a process known as nucleosynthesis, which occurred just a few minutes after the Big Bang. In this short window of time, the universe's elemental composition began to take shape. About 25% of its mass was converted into helium, while hydrogen remained the dominant element. These primordial materials would serve as the raw ingredients for the stars and galaxies that would later populate the cosmos. The universe continued to cool and evolve. By 380,000 years after the Big Bang, it had reached a temperature of approximately 3,000 Kelvin. At this point, the cooler conditions allowed electrons to combine with protons to form neutral hydrogen atoms. This shift allowed light to travel freely through space for the first time, marking the release of the cosmic microwave background radiation, a faint afterglow that continues to provide a snapshot of the universe in its infancy. From these turbulent beginnings, the universe gradually expanded into the vast expanse we observe today. Following the Big Bang, the very first elements formed during nucleosynthesis, the critical phase that occurred just minutes after the initial explosion. As the universe cooled and expanded, protons and neutrons, the fundamental components of atomic nuclei, began to merge. This process, driven by extreme temperature and pressure, led to the fusion of hydrogen nuclei, protons, into helium nuclei, creating the simplest elements in existence. About 3 minutes after the Big Bang, the universe cooled to a point where protons and neutrons could combine, leading to the formation of deuterium, a stable isotope of hydrogen. This milestone enabled further nuclear reactions, allowing deuterium to fuse with additional protons and neutrons, ultimately producing helium nuclei. To a much smaller degree, elements like lithium and beryllium were also synthesized during this early stage. By the end of this process, roughly 75% of the universe's baryonic mass was in the form of hydrogen, while 25% had transformed into helium. This ratio of elements produced in the first few minutes laid the foundational blueprint for the stars that would later emerge. Helium, one of the primordial elements, would play a crucial role in stellar nucleosynthesis, the process by which stars fuse lighter elements into heavier ones. The relatively simple elements created during this short explosive period are often referred to as primordial elements, and they represent the first steps in cosmic evolution. These primordial elements continue to be detectable today. Observations of the cosmic microwave background radiation, as well as the elemental compositions of ancient stars, provide key evidence supporting this scenario. Through these observations, we can piece together a vivid picture of how the very first elements formed and set the stage for the more complex chemical processes that would eventually lead to the creation of galaxies, stars, and ultimately, life itself. The timeline of the universe, as understood through the lens of the Big Bang theory, reveals a remarkable sequence of events that chronicles the dramatic evolution from the universe's inception to its present state. This journey began nearly 13.8 billion years ago with the Big Bang, a singular event that forever changed the course of existence. In an instant, it not only marked the birth of time and space, but also set the stage for the creation of all matter. This event, though hard to imagine, was the catalyst for an expansion so rapid and intense that it reshaped the very fabric of the cosmos. In the first moments following the Big Bang, within the briefest fraction of time, a thousandth of a second, the universe was engulfed by energy. This period, known as cosmic inflation, saw the universe balloon to extraordinary sizes, smoothing out the irregularities that existed in its primordial form. As the universe expanded, it began to cool, and the fundamental forces of nature, like gravity and electromagnetism, separated, laying the groundwork for the universe's later complexities. Just minutes after the Big Bang, nucleosynthesis took place, a process that resulted in the formation of hydrogen and helium, the foundational elements that would serve as the building blocks for everything that followed. As the universe continued to cool and expand, a key moment occurred about 380,000 years later. It was then that electrons and protons combined to form neutral hydrogen atoms, allowing light to travel freely for the first time. This era, known as recombination, marked the release of cosmic microwave background radiation, a faint afterglow of the early universe that still lingers in the present day. As the universe continued to evolve, the first few 100 million years saw another significant transformation, the era of reionization. During this time, the first stars ignited, their powerful radiation illuminating the vast expanse of space. The birth of these stars led to the formation of the first galaxies, which over billions of years grew and evolved into the intricate structures of galaxies, clusters, and superclusters we observe today. This dynamic process set the stage for the cosmic web, a vast interconnected structure composed of galaxies and vast voids. Fast forward to today, and the universe continues to expand. Mysterious forces such as dark energy are pushing it to stretch ever farther, shaping the cosmos in ways that continue to intrigue scientists. While much of the universe's grand design is still shrouded in mystery, the Big Bang Theory offers a cohesive framework for understanding its development. By combining early conditions with the processes that followed, it explains the distribution of matter across the cosmos. In the aftermath of the Big Bang, the universe was nearly homogeneous, uniform in all directions on a grand scale. However, small quantum fluctuations during cosmic inflation created density variations, which would later have profound consequences. As the universe expanded and cooled, these fluctuations in density grew under the influence of gravity. Regions with slightly higher density began to attract more matter, while less dense regions remained relatively unaffected. This gravitational pull led to the formation of gas clouds, which eventually collapsed and coalesced, giving birth to stars and galaxies. Over millions of years, these celestial bodies continued to interact through gravity, forming larger structures like galaxy clusters and superclusters. Cosmic microwave background radiation, which continues to provide a snapshot of the early universe, holds the key to understanding these fluctuations. By studying its faint patterns, cosmologists can trace how matter is distributed across the universe. These subtle variations correlate with the large-scale structures we see today: massive galaxies, clusters, and the sprawling cosmic web. The Big Bang Theory also accounts for the observed abundance of light elements like hydrogen and helium. These elements were forged in the aftermath of the Big Bang during nucleosynthesis. They are the raw materials from which stars form, and thus play a crucial role in the evolution of galaxies and the development of more complex structures in the universe. Through a combination of the early physics of the universe, gravitational dynamics, and careful analysis of cosmic microwave background radiation, the Big Bang Theory provides an effective explanation for the intricate distribution of matter we observe in the cosmos today. The theory ties together the birth of light elements, the formation of celestial structures, and the expansion of space itself into a coherent narrative of cosmic evolution. Despite its successes, the Big Bang Theory is often surrounded by misconceptions. A common misunderstanding is the belief that the Big Bang was an explosion that scattered matter into empty space. In reality, it was an expansion of space itself. There was no central explosion, no singular point from which matter radiated outward. Instead, every point in the universe has been expanding, with galaxies moving away from one another as space itself stretches. Another widespread misconception concerns the size of the universe at the moment of the Big Bang. Some imagine the universe as a tiny point that suddenly exploded. While the universe was indeed incredibly small and dense at its inception, it was not a point in the conventional sense. Instead, it represented the entirety of space, containing all the energy and matter that would eventually evolve into the vast cosmos we observe today. This shift in perspective helps us grasp the true scale and nature of the universe's origin. People often assume that the Big Bang Theory describes the absolute origin of everything, yet it primarily focuses on the evolution of the universe from a hot, dense state. It doesn't provide a definitive answer to what happened before the Big Bang or what could have triggered the expansion. In fact, the very concept of before the Big Bang is tricky, as time itself began as part of the universe at that moment. This leads to questions that blend science with deep philosophical inquiry, questions that remain unresolved and fascinating to this day. Furthermore, some people mistakenly believe the Big Bang was a one-time event, leading to a static universe. In reality, the cosmos continues to expand, and this expansion is not just ongoing, but accelerating, a phenomenon attributed to dark energy. The Big Bang Theory, therefore, is not solely about the past. It also plays a crucial role in shaping our understanding of the universe's future and the ongoing processes that continue to mold its structure. These misunderstandings underscore the importance of continued scientific education and the popularization of complex concepts to foster a deeper understanding of the cosmos. An intriguing alternative to the Big Bang Theory is the cyclic model of the universe. This model proposes that the universe undergoes a series of expansions and contractions, or cycles, rather than having a singular beginning. Each cycle begins with an expansion phase, similar to what we know as the Big Bang, followed by a contraction phase that ultimately brings everything back into a hot, dense state. According to this theory, the universe does not have a definitive beginning or end, but instead follows a perpetual rhythm of birth, death, and rebirth. In the context of the Big Bang, the cyclic model views the event as just one of many in an eternal sequence of expansions and contractions. Each expansion, much like the Big Bang itself, creates the conditions for the formation of new galaxies, stars, and elements. As the universe expands, it cools and evolves into a complex structure. When the expansion slows and reverses, the universe begins to contract, eventually collapsing into a singularity. This contraction then triggers the next Big Bang, igniting the next cycle of expansion. The cyclic model also offers a potential resolution to questions raised by the Big Bang theory, especially regarding the ultimate fate of the universe. While the standard Big Bang model suggests outcomes like heat death or the Big Crunch, the cyclic model envisions a more dynamic outcome. Each cycle could introduce new physical properties or behaviors, possibly explaining the observed acceleration of cosmic expansion due to dark energy. Critics, however, argue that the cyclic model faces significant challenges in explaining certain aspects of cosmic evolution and in aligning with observational data. Nonetheless, it remains a vibrant area of research, with astronomers and theoretical physicists examining its implications for both the origins and the future of the universe. By connecting the Big Bang with subsequent phases of cosmological evolution, the cyclic model forces us to rethink our understanding of time, existence, and the ultimate destiny of the cosmos. Then there's the ekpyrotic scenario, which offers a captivating explanation for what might have existed before the Big Bang, challenging the conventional notion of a singular origin. Rooted in string theory, this model posits that our universe resulted from the collision of two three-dimensional branes, fundamental objects in higher dimensional space. In this view, rather than emerging from a singular point, the universe as we know it is the product of interactions between these branes within a higher dimensional reality. According to the ekpyrotic scenario, the universe before the Big Bang wasn't empty or devoid of structure. Instead, these branes existed within an expansive higher dimensional space. Over time, the branes slowly moved toward each other until their collision triggered the enormous release of energy that led to the expansion we now recognize as the Big Bang. This perspective suggests that the universe's explosive emergence wasn't from absolute nothingness, but from an interaction between pre-existing structures, offering a radically different view from the traditional understanding. Moreover, the ekpyrotic model offers solutions to some of the puzzles that have long plagued cosmologists, such as the uniformity of the cosmic microwave background radiation observed today. By proposing that our universe is just one of many in a higher dimensional space, the ekpyrotic model challenges the notion of a universe that sprang from nothing, instead offering a more complex and interconnected view of the cosmos. The existence and dynamics of branes could, in theory, set the stage for the formation of the observed density fluctuations in the universe, without needing to invoke the rapid expansion that cosmic inflation describes in the standard Big Bang model. While the idea of the erotic scenario remains theoretical and continues to be rigorously scrutinized, it brings a new depth to our understanding of cosmological origins. This model shifts the conversation away from a singular beginning and instead points toward a more intricate interplay of dimensions and structures that existed before our universe even came into being. By exploring this approach, we move from a narrow view of the universe as a single entity that emerged from a definitive Big Bang and into a far broader multidimensional framework. Here, the origins of the cosmos are not seen as a one-off event, but as a complex, evolving process. This shift encourages us to reconsider how time, existence, and the universe itself interact on a foundational level. It's a compelling reminder that cosmology is an ever-expanding field, and each new theory adds layers to the quest to unravel the mysteries of the cosmos. A bold and groundbreaking perspective on the creation of universes comes from physicist Lee Smolin, whose Fen universe theory introduces a radical idea: According to Smolin, universes could emerge not from an initial singularity, but through the process of black holes. Instead of imagining our universe as the first and only one, Smolin suggests that every black hole may give birth to a completely new universe, each with its own unique laws of physics and constants. The theory begins with the collapse of a massive star under gravity's crushing force, forming a black hole. However, within the confines of this black hole, conditions may arise that allow for the creation of new universes. Smolin's model proposes that as the black hole evolves, the matter and energy inside it could contribute to the emergence of a fresh cosmos. Each of these new universes would bear subtle differences, shaped by the characteristics of the parent universe, effectively making each black hole a gateway to an entirely new dimension of existence. This model introduces the idea of a multiverse, an intricate web of interconnected universes, each evolving in tandem with one another. Universes that have the ability to produce black holes would have a higher chance of generating descendant universes. The theory suggests an evolutionary mechanism in which only certain universes, those with the right conditions for black hole formation, would be able to spawn new ones. In this way, Smolin's theory points to a process of cosmic selection. Universes capable of producing black holes are more likely to endure, propagate, and evolve over time. This theory presents a vision of a self-perpetuating cycle of cosmic rebirth, radically altering how we think about the creation, evolution, and fate of our universe. While still largely theoretical and in need of further validation, Smolin's approach challenges our understanding of reality itself. It provokes profound questions about the very nature of existence, urging us to consider the possibility of a vast and interconnected web of universes, each influencing the other in a complex, continuous cycle. This raises new debates in the realm of cosmology, encouraging us to expand our imaginations beyond the traditional models of a singular universe with a singular origin. String theory also plays a pivotal role in enhancing our understanding of the universe's pre-Big Bang state. According to string theory, the fundamental building blocks of reality are not particles, but rather one-dimensional strings that vibrate at different frequencies. These strings exist within a higher dimensional space, one that contains additional dimensions beyond the three of space and one of time that we're familiar with. This framework opens up a wealth of possibilities for understanding what existed before the Big Bang. String theory suggests that the pre-Big Bang universe may have been an entirely different realm, one governed by dimensions and laws of physics we can hardly begin to imagine. One particularly compelling model that emerges from string theory is the ekpyrotic scenario. This theory posits that the Big Bang wasn't the universe's beginning at all, but rather the result of a collision between two three-dimensional brains, short for membranes, within a 10-dimensional space. These brains could have existed prior to the Big Bang, interacting in ways that paved the way for the universe we now know. Such interactions between these brains would have created the dynamic conditions that led to the formation of our cosmos. The ekpyrotic model offers an exciting perspective on the pre-Big Bang universe, suggesting that it wasn't a singular event that suddenly sparked everything into being. Instead, it may have been the result of ongoing interactions between multiple dimensions, each influencing the other in ways that are still beyond our full comprehension. By introducing the idea of brains and multidimensional spaces, this theory provides a rich and layered understanding of how our universe could have emerged, and what might have existed in the void before the Big Bang. Ultimately, these theories, whether the Fenn universe model of black hole births or the ekpyrotic brain collisions, push the boundaries of our imagination. They challenge us to think about cosmology not as a linear timeline, but as a dynamic, multifaceted process that could involve countless universes, interacting and evolving over time. The quest to understand the true origins of our universe is far from over, but these innovative ideas offer a glimpse into a much more complex and interconnected cosmic reality than we ever thought possible. String theory offers a fascinating framework for understanding the universe's most extreme phenomena, particularly those that challenge traditional models. In conventional theories, gravity's quantum aspects struggle to reconcile with the intense conditions found near singularities, like those theorized to exist at the heart of black holes or at the dawn of the Big Bang. String theory, however, provides a potential mechanism to navigate these complexities, suggesting that instead of a definitive singular beginning, the universe could have undergone a series of transformations. This idea reshapes how we perceive the very nature of time. Under this lens, the concept of before the Big Bang may no longer apply, as time, as we understand it, could be a product of deeper, more fundamental processes involving strings. In this model, the universe isn't a one-time event, but a dynamic system of constant change, evolving through various stages that transcend the linear flow of time. Furthermore, string theory introduces the possibility of a multiverse, a landscape of different universes, each governed by its own set of physical laws and constants. This concept invites us to consider the pre-Big Bang universe not as a singular origin, but as one of many potential configurations in a vast cosmic tapestry. These parallel universes could be shaped by the intricate interactions of strings, further deepening our understanding of cosmic origins. Rather than a void or absence, string theory proposes that the universe before the Big Bang could have been teeming with dynamic interactions, an intricate prelude to the cosmos we inhabit today. One of the most unconventional yet captivating theories regarding the universe's evolution comes from physicist Roger Penrose, who introduced the concept of conformal cyclic cosmology, CCC. This theory envisions the universe undergoing an infinite series of cycles, each one transitioning from an extremely hot, dense state to a cold, expansive one. In CCC, the end of one cosmic era doesn't signify an absolute end, but rather a smooth and continuous transformation into the next epoch. Time, in this view, becomes less of a linear progression and more of an evolving journey, conformally altered with each new cycle. Penrose's vision suggests that as the universe expands and cools, galaxies and stars will fade away, leaving a uniform, featureless state dominated by low-energy radiation. In this far-future version of the universe, referred to as the cosmic no-air state, the distinctive properties of matter and energy dissipate. What remains is a homogeneous environment where the curvature of space and time becomes so simplified that the very concepts of distance and time lose their conventional meaning. Penrose introduces the idea of a conformal transformation, a mathematical process that resizes the properties of space-time, preserving angles while eliminating traditional metrics of space. This transformation offers a bridge between the end of one universe and the beginning of another, creating a seamless transition between cycles. The end of one era thus provides the fertile ground for a new beginning, effectively resetting the cosmos to a new state. What emerges from an intense, hot, and dense phase can be viewed as the rebirth of the universe, suggesting an eternal cyclical nature rather than a singular, linear origin. Although CCC remains speculative, it challenges conventional ideas of a singular Big Bang event and provides an intriguing perspective on the nature of time, existence, and cosmic evolution. Penrose's theory proposes that the universe, far from being a single finite event, may be part of an endless cycle of creation, evolution, and rebirth. In a similar vein, loop quantum cosmology, LQC, offers yet another perspective on the universe's origins, one that incorporates principles from loop quantum gravity. This theory seeks to unify quantum mechanics and general relativity, offering a radically different take on space and time. According to LQC, space and time are not continuous, but instead quantized, resembling a network of discrete loops. This quantization has profound implications for how we understand the conditions of the early universe, especially when considering what happened before the Big Bang. In LQC, the universe doesn't collapse into a singularity at the moment of the Big Bang. Instead, as it contracts under the influence of gravity, it reaches a point where quantum effects take over, preventing the infinite density typical of a singularity. Rather than an abrupt collapse, the universe experiences a bounce, transitioning from contraction to expansion in a smooth, continuous process. This model suggests that there was indeed a pre-Big Bang state, one characterized by high energy and density, yet it avoids the paradoxical features of traditional singularities. The idea of discrete space-time also challenges our understanding of time itself, suggesting that in such extreme conditions, time could behave very differently, potentially disrupting our conventional understanding of causality. In this scenario, the shift from contraction to expansion occurs without the sharp discontinuity traditionally associated with singularities. The universe, rather than having a definite beginning, could have experienced an ongoing cyclical evolution where each phase naturally flows into the next. This idea offers a more fluid, continuous view of the universe's evolution, proposing that the boundaries of time and space are far more malleable than we have ever imagined. Through these theories, string theory, conformal cyclic cosmology, and loop quantum cosmology, we are presented with radically new ways of thinking about the cosmos. The implications challenge our deepest assumptions about the nature of time, space, and existence itself, offering a future where the universe is not a single, finite event, but part of an endless, evolving cycle. Loop quantum cosmology offers profound insights into the behavior of gravity at the quantum level. It reveals that quantum gravitational effects can alter the very structure of spacetime, suggesting that the geometry of the universe was radically different in its earliest moments compared to what we understand through classical physics. In this light, loop quantum cosmology challenges our traditional views, presenting a universe in its infancy as a dynamic, evolving state where the boundaries of time and space dissolve into a continuum of quantum states. This model of the universe's birth paints a picture far richer than the simple beginning we once imagined, one where time and space as we know them are but emergent properties. Through this lens, we gain a more profound understanding of the pre-Big Bang universe. It becomes a kind of quantum stage where the classical notions of beginning and end blur, and what we now perceive as the present is only a small fraction of a much larger cosmic dance. Loop quantum cosmology does not just reshape how we think about the past, but it also calls into question the very nature of reality itself, offering us a glimpse into the infinite possibilities that quantum mechanics can provide. Meanwhile, the no-boundary proposal, introduced by physicists Stephen Hawking and James Hartle, takes a radically different approach to understanding the universe's origins. According to this groundbreaking theory, the universe has no boundary or edge in a spatial sense, which challenges the traditional idea of a specific moment of creation. Instead of a singular point of origin, the no-boundary proposal suggests that the universe has a smooth, finite geometry, one that can be described mathematically by a complex manifold, a kind of surface that represents the universe's underlying structure. The proposal further entwines the concepts of space and time, especially during the universe's earliest moments or when energy levels were unimaginably high. Hawking and Hartle liken the early universe to a sphere. Just as a sphere has no edges, the early universe could be thought of as a rounded, smooth shape, without a clear point of beginning. This view eliminates the need for a singular start to the cosmos, and instead invites us to think of the universe as timeless, with space and time themselves merging in a way that makes any distinctions between them disappear. This idea, profound as it is, carries far-reaching implications for our understanding of cosmology. The no-boundary proposal suggests that the universe could have emerged spontaneously from a quantum vacuum state, without any external cause or trigger. Instead of a creation event that must be set in motion by an outside force, the universe could have simply come into existence in a seamless, almost effortless way. This concept resonates with some of the ideas in cosmic inflation theory, where quantum fluctuations lead to the uniformity of the universe we observe today, allowing for a universe that appears to pop into existence, much like particles can emerge out of nothing. Through this shift, the no-boundary proposal challenges classical notions of causality in the cosmic timeline, presenting the universe's origins as part of a quantum process. Time, once thought of as a steady, linear progression, becomes entangled with space, allowing for a deeper exploration of how the universe could have arisen. This theory invites a more fluid understanding of cosmology, one that harmonizes the principles of quantum mechanics and general relativity. It is this delicate balance that opens new doors for exploration, suggesting that the foundations of reality are far more complex and mysterious than we could have ever imagined. The implications of the no-boundary proposal go beyond theoretical physics. It offers a new framework for thinking about the universe itself, encouraging a re-examination of the very concepts of creation, time, and the fabric of existence. In many ways, it represents an extraordinary leap forward in our understanding, providing a fresh perspective on the cosmos that could shape the direction of scientific inquiry for years to come. At the same time, the multiverse theory offers an even broader perspective on pre-Big Bang existence, suggesting that our universe may not be the only one. Instead, it might be part of a vast multiverse, an array of countless universes, each governed by its own unique laws of physics, constants, and properties. This theory challenges the singularity of our universe, proposing that the origins of our cosmos could be just one thread in a much larger, more complex tapestry of universes. In the multiverse scenario, the Big Bang could simply represent the specific event that gave birth to our universe within a much larger multiversal framework. Universes, or bubbles, could have formed simultaneously, each with vastly different physical conditions and properties. These bubbles might have expanded and evolved in entirely different ways, creating realms that are as distinct from our own as night is from day. The multiverse theory suggests that just as our universe underwent a rapid inflationary period, so too could other universes have emerged through similar processes, each with its own unique set of circumstances. Exploring the multiverse opens up a fascinating range of possibilities, not only for the study of the origins of our universe, but also for the understanding of what may have existed before the Big Bang. What we call the beginning of the cosmos could just be one of many points in an ongoing, ever-expanding multiversal evolution. In this scenario, the boundaries of what we consider reality are stretched far beyond what we could have imagined, revealing a deeper, more intricate structure to existence. The implications are not just theoretical, they offer us a new way of understanding the very nature of reality itself, inviting further investigation into the conditions that might precede the Big Bang and the nature of the universes that may lie beyond our own. Quantum mechanics is pivotal to the multiverse theory, especially through interpretations such as the many worlds hypothesis. In this view, every quantum event leads to the branching of outcomes, creating parallel universes where alternate histories unfold. This concept of branching universes introduces a dynamic, ever-evolving framework, suggesting that the pre-Big Bang state may have involved countless potential universes. These universes could have collided, merged, or coexisted before settling into the structure we recognize today. Moreover, the multiverse theory provides answers to questions about the fine-tuning of our universe's physical constants. With an infinite array of universes, each having its own set of parameters, it's possible that our universe is just one in a vast landscape where life emerged in conditions that supported it. In this way, exploring the multiverse not only offers new insights into the nature of reality, but challenges the traditional notion of a singular, unique origin. The multiverse theory deepens our understanding of pre-Big Bang existence, envisioning a cosmos brimming with possibilities. It suggests that the emergence, evolution, and diversity of universes go beyond our own, encouraging a re-examination of the fabric of reality. It invites us to reflect on the fundamental principles that govern existence, across an expanse that we are only beginning to grasp. One of the boldest challenges to conventional physics is the varying speed of light theory, VSL, which posits that the speed of light is not fixed, as traditionally understood, but can fluctuate depending on the conditions of the universe. This theory directly confronts the postulate of special relativity, which maintains the speed of light in a vacuum as a universal constant. VSL suggests that in the early universe, particularly during events like inflation, the speed of light may have been vastly different from what we observe today. If the speed of light were indeed higher during the universe's infancy, it could have enabled light to travel faster than it does now, resulting in the rapid establishment of uniformity across vast regions of space. This theory could offer an alternative explanation for the observed homogeneity of the cosmic microwave background radiation and resolve inconsistencies within the traditional Big Bang model, particularly regarding cosmic inflation. The rapid spread of light in the early universe, enabled by a variable speed of light, might have achieved the same effects as inflation without necessitating the extreme expansion commonly associated with this theory. Additionally, the VSL theory offers new perspectives on early cosmic events, such as the formation of structures and the behavior of fundamental forces. By allowing the speed of light to vary, the theory could alter the dynamics of particle interactions at high energies, which would, in turn, influence how matter and energy evolved in the universe's formative periods. However, the VSL theory is not without its critics. The concept raises profound questions about the mechanics of physics as we currently understand them, particularly with respect to causality and the established principles of relativity. Evidence supporting the idea of varying light speed remains sparse, and ongoing research continues to explore the possible consequences of this theory within the broader framework of cosmology. Nonetheless, the VSL theory stands as a bold re-examination of physics, suggesting that the universe may operate according to more complex and nuanced rules than we have imagined. It challenges the foundational assumptions of the Big Bang model and invites a deeper exploration of the universe's origin, structure, and evolution. Eternal inflation offers a compelling alternative to the traditional Big Bang model. According to this theory, the universe did not emerge from a singular point or an initial explosion, as the Big Bang suggests. Instead, the universe experienced a perpetual inflationary phase, causing vast regions of space to expand at incredible rates, eventually leading to the creation of multiple universes within a grand multiverse. Before the formation of our observable universe, the cosmos existed as an infinite expanse filled with energy and potential. Within this boundless space, microscopic fluctuations in energy could have led to the formation of bubble universes, each with its own unique set of physical laws and constants. Our observable universe is just one of these bubbles, which eventually ceased its inflationary expansion and began cooling, allowing matter to form. This model explains why our universe appears so flat and homogeneous on large scales, traits that emerged from the rapid inflationary expansion. The ongoing process of eternal inflation would theoretically continue forever, generating countless regions of space that could eventually form their own distinct pocket dimensions. Each of these regions would possess unique characteristics governed by different physical laws, creating an infinite variety of cosmic environments. Moreover, this framework provides a profound insight into some of the most fundamental questions about the universe's inception. It proposes that the remarkable uniformity observed in the cosmic microwave background radiation, a remnant from the early universe, can be traced back to the quantum fluctuations that occurred during inflation. These fluctuations, which permeated all regions during this crucial phase, helped to seed the observable universe as we know it. As such, the state of the universe before our current observable reality can be understood as part of an endless cycle of inflationary events, each one setting the stage for the unfolding tapestry of universes within the larger multiverse. Quantum fluctuations are fascinating phenomena that emerge at the subatomic level, where particles and energy levels undergo unpredictable changes due to the inherent uncertainties defined by quantum mechanics. In fact, according to the principles of quantum theory, even empty space is not truly empty. It is filled with virtual particles that momentarily appear and disappear. This constant activity within the vacuum gives rise to brief yet significant fluctuations in energy. These fluctuations play a crucial role in shaping the universe's origin, particularly in the context of cosmic inflation theory. When the universe underwent its rapid early expansion, even the smallest variations in energy density were amplified by the inflationary process. This amplification stretched tiny quantum fluctuations across the vast expanse of space, creating the uneven distribution of matter and energy. Essentially, these fluctuations, originating from the quantum realm, were stretched over unimaginable distances, laying the groundwork for the formation of galaxies, stars, and the grand structures that characterize the cosmos. An intriguing aspect of quantum fluctuations is their ability to create bubbles of space, each one potentially evolving into an entire universe. In the theory of eternal inflation, different regions of space can experience distinct fluctuations, leading to the creation of diverse universes, each governed by its own set of physical laws. This notion aligns with the concept of the multiverse, where our universe is merely one among many, each birthed by random quantum events. Thus, The relationship between quantum fluctuations and the origin of the universe represents a fascinating intersection between quantum mechanics and cosmology. It underscores how the very building blocks of reality can influence the vastness and complexity of the universe we inhabit. These fluctuations provide us with a glimpse into the mechanisms that could drive cosmic growth and structure, revealing the unpredictable nature of existence itself. Heisenberg's uncertainty principle is a cornerstone of quantum mechanics, stating that certain pairs of physical properties, such as position and momentum, cannot be precisely measured at the same time. This principle highlights the inherent limitations in our ability to predict and measure the behavior of particles at the quantum level. In the context of the early universe, this principle has profound implications for understanding its formation and evolution. In the moments immediately following the Big Bang, when the universe was incredibly dense and hot, quantum effects dominated its behavior. During this period, the uncertainty principle suggested that fluctuations in energy and density were unavoidable. The enormous energy present in such a compact environment allowed particles to be spontaneously created and annihilated, resulting in a chaotic state where not only matter was fluctuating, but space itself was undergoing fluctuations. These fluctuations, driven by the uncertainty principle, played a pivotal role in cosmic inflation. As the universe underwent rapid expansion, small variations in energy density, fueled by quantum fluctuations, were stretched across vast distances. These fluctuations eventually seeded the large-scale structures of the universe, such as galaxies and clusters of galaxies. Without Heisenberg's uncertainty principle, the very mechanism that enabled the instability and variations necessary for the formation of cosmic structures would have been absent. Thus, the uncertainty principle does more than highlight the limitations of our measurement abilities. It is a crucial player in the dynamic interplay between quantum mechanics and cosmology, emphasizing that the early universe was not a calm, orderly space, but a dynamic, unpredictable environment shaped by the very uncertainties that govern the behavior of particles at the smallest scales. This interplay sheds light on how the universe's vastness and complexity arose from the quantum processes at its birth. Quantum tunneling is another fascinating phenomenon in quantum mechanics, where a particle can pass through a potential energy barrier, even if it does not have enough energy to surmount that barrier in classical terms. This behavior arises due to the wave-like properties of particles, allowing for a probability of finding the particle on the other side of the barrier, despite classical expectations. In the context of the universe's birth, quantum tunneling is thought to have played a crucial role in scenarios involving the creation of the universe from a vacuum state before the Big Bang. Some theories suggest that the universe may have originated from a state of nothingness, a vacuum that was unstable. Quantum fluctuations could have facilitated the appearance of a small amount of energy from this vacuum, which was sufficient to trigger inflation. Once this tunneling event occurred, the energy could have passed through the barrier of the vacuum state, leading to the creation of a bubble where the universe began to expand. This newly formed region could have undergone rapid inflation, setting into motion the expansion that would eventually give rise to the universe we see today. The energy from this tunneling event would have caused the bubble of space to inflate dramatically, shaping the fabric of space-time and transforming the energy into matter. This idea offers a potential solution to one of the universe's greatest mysteries. How could an extremely dense and hot state emerge from near total nothingness without violating the principles of quantum mechanics? Quantum tunneling, with its paradoxical nature, might hold the key to understanding the birth of our universe, illustrating that even from the most improbable of events, the vast cosmos could unfold. Quantum tunneling has far-reaching implications beyond the boundaries of particle physics, potentially offering a key to understanding some of the universe's most fundamental processes. This phenomenon, where particles pass through barriers that classical physics suggests should be insurmountable, could be a vital piece in the puzzle of cosmic origins. For instance, the formation of black holes and the behavior of particles in extreme energy environments may be better explained through tunneling processes, casting new light on the intricate mechanics governing the cosmos. In this way, quantum tunneling not only provides a window into the origins of the universe, but it also extends its influence into cosmology and particle physics, offering a glimpse into the probability-driven dance that governs the deepest layers of reality. The interplay of chance and certainty in this realm may help us unravel questions that have remained elusive for centuries. Similarly, quantum entanglement, a phenomenon where particles become intertwined in such a way that the state of one particle instantly affects another, regardless of distance, defies our everyday intuitions about communication and locality. The immediate influence of one particle on another, no matter how far apart they are, challenges our understanding of reality and space itself. In the context of the early universe, this bizarre connection could have profound implications, particularly when we consider the uniformity of the cosmic microwave background radiation, the afterglow of the Big Bang. As the universe expanded and cooled rapidly following the Big Bang, quantum entanglement might have played a crucial role in ensuring that different regions of space communicated information about their respective states. This shared exchange of information could offer an explanation for the apparent uniformity of the universe on large scales, despite the existence of extreme fluctuations. During the inflationary phase of the universe, a brief but rapid expansion, entangled pairs of particles could have emerged from fluctuations in energy. As the universe continued to inflate, these entangled particles expanded with space itself, potentially influencing each other's properties even as they grew increasingly distant. The significance of entanglement reaches beyond this, touching on theories of the multiverse. If our observable universe is merely one of many bubbles formed by an eternal inflationary process, quantum entanglement could point to intricate relationships between these universes, facilitating information transfer or correlations across them. Such ideas expand the boundaries of our understanding of space, time, and the very nature of reality. They suggest that entanglement is not just a feature of quantum mechanics, but possibly a vital thread in the complex fabric of cosmology, connecting the earliest stages of the universe with its continued evolution. The Wheeler-DeWitt equation offers another fascinating entry point into this deeper exploration of the cosmos. Developed by John Archibald Wheeler and Bryce DeWitt in the 20th century, this equation represents an attempt to merge the principles of quantum mechanics with those of general relativity. Unlike many equations that describe the behavior of individual particles, the Wheeler-DeWitt equation takes a bold step by attempting to describe the quantum state of the universe as a whole, capturing the interplay of geometry, matter, and energy. At the heart of the equation lies a concept that challenges our conventional understanding of time. The Wheeler-DeWitt equation describes the evolution of the universe's quantum state without relying on time as a variable. In this framework, the universe is seen as existing in a superposition of all possible states, with its geometry and matter constantly shifting between countless configurations. This approach reflects a deeper, more fundamental view of the universe, where the conventional notion of time may not be an intrinsic property, but rather an emergent phenomenon, an idea that suggests time itself may arise from more fundamental quantum processes. This notion opens the door to a radical reinterpretation of the universe's origins. Rather than relying on a classical time variable, the equation provides a framework for exploring the birth of the universe itself, raising profound questions about what before the Big Bang truly means. Although the equation's theoretical elegance is undeniable, it also poses significant challenges, particularly in its interpretation and practical application. Researchers continue to grapple with the equation's implications, particularly in the study of black holes, cosmological phenomena, and the very structure of space-time. Quantum foam theory, proposed by John Wheeler, offers yet another radical perspective on the nature of space and time. According to this theory, at the smallest scales, near the Planck length, around 10 to the power of negative 35 meters, space-time is not the smooth, continuous fabric we perceive at larger scales. Instead, it is a frothy, bubbling structure characterized by dynamic fluctuations. At this scale, particle-antiparticle pairs form and annihilate in an ongoing energetic dance, creating a state of chaos and turbulence in the very fabric of space-time itself. Before the Big Bang, The quantum foam theory suggests that the universe may have existed in a radically different state than the one we observe today. The turbulence of this quantum foam could have played a role in shaping the early conditions of the universe, offering insights into the mysterious processes that governed its creation. This radical perspective on the nature of space-time challenges our deepest assumptions, urging us to reconsider what we know about the universe and its origins. Together, these ideas, quantum tunneling, entanglement, the Wheeler-DeWitt equation, and quantum foam theory, represent some of the most intriguing and complex areas of modern physics. They push the boundaries of our understanding, challenging us to think beyond the limits of classical physics and to consider a universe that is far more interconnected and dynamic than we ever imagined. As we continue to probe these mysteries, the intricate dance of particles, space, and time unfolds, offering glimpses into the very nature of reality itself. Before the Big Bang, the landscape of space and time was dramatically different from what we understand today. Classical cosmological theories suggest that this was a point of transition, but the concept of quantum foam paints an even more fascinating picture. It proposes that the very fabric of reality was dominated by quantum effects, where conventional notions of time and space became meaningless. In place of a stable, smooth continuum, there existed a tumultuous, ever-fluctuating sea, a quantum playground where space-time itself could bend, twist, and warp. This was a primordial stage where the building blocks of reality were not yet formed, but were instead constantly in flux. In this chaotic environment, quantum fluctuations, tiny, unpredictable disturbances, could have created the conditions necessary for the Big Bang. The quantum foam might have acted as a crucible for these fluctuations, amplifying them to such an extent that they set the stage for the birth of cosmic inflation. As inflation rapidly expanded the universe, smoothing out the irregularities on large scales, the turbulent microcosm of the quantum foam transitioned into the more ordered universe we see today. The immense energies at play during this transition could have fueled the creation of matter and energy, marking the moment when the universe shifted from a quantum state into the classical realm we experience. Quantum foam enriches our understanding of the early universe by suggesting that the vacuum prior to the Big Bang was anything but empty. It was an active, dynamic landscape where fluctuations in space-time might have shaped the very essence of existence. This challenges our basic assumptions about reality and opens up fascinating new possibilities regarding the origins of the universe and the nature of reality itself. At the heart of this exploration lies quantum gravity, a theoretical framework that aims to bridge the gap between quantum mechanics and general relativity. These two pillars of modern physics describe different aspects of the universe. General relativity explains the curvature of space-time on large scales, such as around galaxies and black holes, while quantum mechanics governs the behavior of subatomic particles. Reconciling these two theories into a unified framework is one of the most pressing goals in physics. The problem lies in the fact that they operate under fundamentally different principles, making their integration incredibly complex. Quantum gravity is especially crucial for understanding the early universe, as it involves a period of extreme conditions, high densities and temperatures, where both quantum and gravitational effects were significant. In this realm, classical physics breaks down, and a theory that incorporates both the principles of gravity and quantum mechanics is needed to describe the universe's behavior accurately. Without this, we cannot fully comprehend key events such as the birth of the universe or the mechanisms behind cosmic inflation. Several approaches to quantum gravity have been proposed. These include string theory, loop quantum gravity, and others, each offering unique insights into how space-time might behave at the quantum level. For example, in loop quantum gravity, space-time is seen as composed of discrete units, suggesting that geometry itself is quantized. This perspective could help explain phenomena such as how the universe avoids singularities, those infinitely dense points in space-time, such as those at the center of black holes or at the very beginning of the universe, where our classical understanding fails. By investigating these theories, physicists hope to unravel the mysteries of quantum gravity and gain deeper insights into the nature of reality. revealing how the universe transitioned from a state of quantum chaos to the ordered cosmos we observe today. One of the most fascinating realms of quantum gravity lies at the Planck scale, roughly 10 to the power of negative 35 meters. At this incredibly tiny scale, both quantum mechanics and gravitational forces intertwine in profound ways. Spacetime no longer behaves as a smooth, continuous entity, but rather exhibits a frothy, foamy structure. This quantum foam suggests that fluctuations occur at a rapid pace, influencing our understanding of the Big Bang in several key ways. Firstly, quantum effects at this scale imply that the universe before the Big Bang may have been in a highly unstable and chaotic state. It was a realm of extreme energies and constant fluctuations, an environment in which space-time itself could rapidly change. The concept of quantum fluctuations means that regions of space could experience spontaneous bursts of energy, creating the ideal conditions for the birth of the universe. In this context, the Big Bang can be viewed not as a singular, isolated event, but rather as the natural culmination of these underlying quantum processes. Secondly, quantum gravity theories offer a potential resolution to the problem of singularities. These are the points in space-time where densities and curvatures become infinite, such as at the centers of black holes or at the very beginning of time itself. At the Planck scale, quantum gravity suggests that space-time behaves differently. Rather than collapsing into singularities, the quantum nature of space-time may prevent this by allowing for a smoother transition from extreme density to the expansive universe we now observe. This shift could be the key to understanding how the universe avoided catastrophic breakdowns and instead unfolded into the cosmos we know today. As we delve deeper into the mysteries of quantum gravity, we are not merely attempting to understand the early universe. We are trying to unlock the very nature of reality itself, offering the possibility of a more complete and unified view of the cosmos, one that could reshape our understanding of existence and our place within it. The study of quantum foam, singularities, and the intersection of quantum mechanics with gravity presents an exciting frontier, promising to reveal new truths about the origins and structure of the universe. The dynamic relationship between quantum effects and gravitational forces plays a critical role in shaping the universe's structure. As quantum fluctuations ripple through space, their influence stretches across the cosmic expanse, especially during the rapid expansion known as cosmic inflation. These minute variations in density give rise to the larger structures we observe today: galaxies, clusters of galaxies, and the vast cosmic web that we are just beginning to understand. At the very heart of this process lies an understanding of the universe's initial conditions. Exploring these phenomena at the Planck scale, the realm where quantum mechanics and gravity converge, opens a window into the early universe. Far from a static beginning, the universe's origins were anything but predictable. Quantum fluctuations shaped the dense, hot state of the cosmos, allowing variations that would eventually lead to the formation of structure. These initial irregularities, small as they were crucial for the evolutionary path that gave rise to the universe as we know it. By incorporating quantum mechanics at this scale, we gain a deeper comprehension of the Big Bang itself, offering answers to long-standing questions about cosmic singularities and the very fabric of space-time. This exploration offers a dramatic challenge to our classical intuitions. The universe we observe today, with its galaxies, stars, and black holes, appears to follow the predictable laws of classical physics. However, when we venture into the quantum domain, these rules break down. At scales smaller than atoms, the universe is governed by bizarre, counterintuitive behaviors. Yet, as we look at the cosmos on a large scale, we see a more structured, classical reality. This duality compels us to rethink our assumptions and consider radically new theories that could reshape our understanding of both the universe's origins and its ongoing evolution. One such concept that helps bridge the gap between quantum and classical physics is decoherence. Decoherence is the process by which quantum systems transition into a classical state as they interact with their environment. In its quantum state, a system can exist in a superposition, simultaneously in multiple possible states, like waves and particles. However, once the system interacts with external factors such as particles, radiation, or even measurements, the superposition collapses. The result is a classical state, where the system behaves predictably according to classical laws. This shift from quantum behavior to classical behavior is crucial for understanding how the universe evolved from its early chaotic beginnings into the structured and familiar reality we experience today. Early in the universe's history, interactions among particles and fields were marked by high levels of entanglement and superpositions. As the universe expanded and cooled, interactions between particles increased in complexity, causing these quantum systems to lose their coherence and behave in more classical ways. Essentially, the universe began to choose definite states, with systems no longer existing in overlapping quantum possibilities. In cosmology, decoherence provides a framework for understanding how the universe transitioned from a sea of quantum possibilities into the ordered structures we see today. It's not about determining the exact outcome of every event, but explaining how, through environmental interactions, a range of potential states can collapse into a single, observable reality. This transformation from quantum to classical behavior is vital for explaining not only the formation of galaxies, but also how we perceive everyday phenomena. It shows how classical reality emerges from the strange world of quantum mechanics and helps us bridge the gap between abstract theory and practical observation. At the same time, decoherence points toward a deeper insight into reality itself. The process underscores the importance of interactions between systems and their environments, suggesting that the nature of these interactions plays a key role in the universe's evolution. In fact, as the universe expanded, the emergence of classicality provided the foundation for the cosmos we observe, with matter and energy taking more predictable and structured forms over time. The holographic principle, a groundbreaking concept in theoretical physics, further enriches our understanding of the universe's origins and evolution. First developed through the work of physicists Gerard 't Hooft and Leonard Susskind, the holographic principle suggests that all the information within a given volume of space can be encoded on its boundary. In essence, it proposes that what we experience as three-dimensional space may be a projection of information that actually resides in two dimensions, much like a hologram. The implications of this principle are profound, especially when considering the early universe. During the period of cosmic inflation, when temperatures and densities were extreme, the universe was expanding rapidly. Traditional views of space suggest that information about the universe's quantum state would reside within its three-dimensional volume. However, the holographic principle posits that this information could instead be encoded on the two-dimensional boundary of the universe. This shift in perspective challenges conventional thinking and invites new ways of understanding the behavior and structure of space-time itself. The holographic principle is not just a theoretical curiosity. It carries significant implications for how we think about the early universe and the forces at play during its formation. For example, as the universe expanded, the information about quantum states and the properties of space-time may have been preserved on this boundary, influencing how structures such as galaxies and cosmic matter evolved as the universe cooled. By linking space-time to this boundary, the holographic principle suggests that quantum gravity and the very structure of space-time may be fundamentally different from what we had imagined. The connection between the holographic principle and cosmic inflation opens a fascinating new chapter in our understanding of the universe's beginnings. It offers a fresh perspective on how the universe may have been structured at its inception and how information about its quantum states could have shaped its development. If proven, it could provide groundbreaking insights into how the universe's most fundamental properties were established during the earliest moments of its existence, potentially leading to new discoveries about the nature of reality itself. When we delve into the fascinating implications of black holes, we confront a mind-bending paradox: the fate of information that falls into them. According to the holographic principle, this information is not lost. In fact, it suggests that even as objects spiral into a black hole, the essence of their data persists in some form, preserved beyond the event horizon. This idea holds the key to unraveling what has come to be known as the information paradox, a puzzle that has baffled physicists for years. The holographic principle, therefore, serves as a vital stepping stone in the search for a unified theory of gravity that can harmonize with quantum mechanics. Such a theory would be essential for understanding the primordial conditions of the universe and its subsequent evolution. At its core, the holographic principle offers a transformative lens through which we can view the relationship between space, information, and physical reality. By suggesting that our universe might be described as a hologram, where all the information contained within it is encoded on a distant boundary, this principle redefines our approach to the cosmos. It challenges traditional boundaries, inviting us to reimagine the fundamental nature of the universe itself. As physicists explore this concept, it opens up new realms of possibility, encouraging them to probe deeper into the mysteries that govern the cosmos. In parallel to these theoretical advances, scientists are using advanced computational techniques to simulate the very moments following the Big Bang. These simulations are pivotal in exploring the early universe's conditions, allowing researchers to examine processes that cannot be directly observed. The task of constructing such simulations begins with theoretical physics, where scientists develop models based on the current understanding of cosmology and particle physics. These models take into account the complex interplay of matter, energy, and gravity, especially under the extreme conditions that existed in the universe's infancy. Since these scenarios are governed by highly complex equations, analytical solutions are often out of reach. Instead, scientists rely on numerical methods to solve these equations, especially when faced with the high energy and high density environments that characterize the early universe. Once the equations are in place, powerful supercomputers step in to run simulations, tracing the evolution of unformed matter, radiation, and even the fabric of space-time itself. These simulations are incredibly diverse, allowing scientists to explore various cosmic scenarios. They can model the rapid expansion of the universe during cosmic inflation, the development of primordial fluctuations, and the formation of large-scale structures, such as galaxies. By tweaking initial conditions and comparing the results with real-world observations, scientists can refine their models, inching closer to an accurate picture of the universe's evolution. But the exploration doesn't end there. Alongside cosmological simulations, researchers also simulate particle interactions in high-energy environments, mimicking the conditions present in the early universe. These particle physics simulations delve into the behavior of fundamental particles during extreme conditions, shedding light on the forces at play as the universe cooled and matter began to take shape. The insights gleaned from these simulations provide an invaluable understanding of how the universe's most basic components evolved. By analyzing the formation of galaxies, the development of cosmic background radiation, and the shaping of the universe's overall structure, these models help researchers track the universe's growth over billions of years. These simulations don't just build theories. They provide a platform for verifying those theories by comparing them with observational data from telescopes and cosmic measurements. When the simulated results align with actual observations, they offer a powerful confirmation of our understanding of cosmic evolution. One specific tool central to this kind of research is the n-body simulation. This computational method is used to study the dynamics of systems composed of multiple gravitationally interacting bodies, whether those bodies are galaxies, stars, or dark matter. The n in n-body refers to the number of objects in the system, which can range from a few to billions. These simulations allow scientists to explore the gravitational interactions between objects and how structures evolve over vast cosmic timescales. In the realm of cosmic structure formation, n-body simulations are indispensable. They help model the behavior of matter in the universe, particularly dark matter, which constitutes roughly 24% of the universe's mass energy content. By representing each dark matter particle as a distinct element within the simulation, researchers can track how these particles cluster together over time due to gravity. This process is fundamental to understanding how galaxies and other large-scale structures form, evolve, and interact. The growth of these gravitational structures driven by dark matter is what has shaped the universe into the sprawling cosmic tapestry that we observe today. In this way, The combination of theoretical physics and sophisticated computational techniques opens a window into the universe's most enigmatic and distant past. Through these tools, scientists continue to push the boundaries of what we know, gradually uncovering the secrets of the universe's origins and its remarkable evolution over billions of years. The simulations begin with an initial distribution of particles designed to reflect the primordial conditions of the early universe. Researchers typically rely on a cosmological model rooted in the standard model of cosmology, incorporating key parameters such as the density of matter, dark energy, and the curvature of space itself. By running these simulations over the course of billions of years, scientists can trace the evolution of initial density fluctuations, observing how these small irregularities gradually transform into massive cosmic structures like galaxy clusters and superclusters. N-body simulations provide invaluable insights into the fundamental workings of the universe, shedding light on a range of cosmic phenomena. One of the most significant contributions is the modeling of the cosmic web, the vast interconnected structure that forms the backbone of the universe. This network consists of galaxies aligned in sprawling filaments, separated by enormous voids of empty space. N-body simulations also help scientists understand complex processes like gravitational lensing, the peculiar behavior of galaxies within clusters, and the intricate dynamics of galaxy mergers. By comparing the results of these simulations with real-world observational data gathered from telescopes and large-scale surveys, researchers can continuously refine their models. This process not only enhances our understanding of the universe's evolution, but also sharpens our knowledge of elusive entities like dark matter, while providing deeper insights into the forces shaping cosmic evolution. The nature of dark matter and its role in the universe remains one of the most profound mysteries in cosmology. Although invisible to traditional methods of detection, dark matter accounts for roughly 24% of the universe's total mass energy content. In cosmological models, dark matter is treated as a non-interacting substance that influences the dynamics of the cosmos primarily through its gravitational effects. These simulations show that dark matter plays a crucial role in the formation of galaxies and the large-scale structure of the universe, despite its elusiveness. To incorporate dark matter into these models, scientists study its gravitational influence on visible matter. One key area of focus is the rotation curves of galaxies. When observing the movement of galaxies within clusters, scientists noticed discrepancies. The gravitational pull was stronger than what could be explained by the visible mass alone. This leads to the inevitable conclusion that there must be an unseen form of mass, exerting influence through gravity, but remaining undetectable by traditional observation methods. To accurately reflect the pervasive influence of dark matter, cosmological models use N-body simulations to simulate the gravitational interactions between vast quantities of dark matter and ordinary baryonic matter. By doing so, they can offer a more comprehensive understanding of the universe's composition, behavior, and ongoing evolution, deepening our grasp of how the cosmos continues to unfold. The lambda-cold dark matter, LCDM model, often regarded as the dominant framework in cosmology, offers a profound understanding of the universe's large-scale structure and its evolution over time. At the heart of this model are two pivotal components: dark energy, represented by the cosmological constant lambda, and cold dark matter, a mysterious form of matter that interacts predominantly through gravity. This cosmological model has emerged as the prevailing paradigm for explaining the observed acceleration in the universe's expansion, a phenomenon attributed to the repulsive force of dark energy. Dark energy, which accounts for roughly 72% of the universe's total mass energy density, remains one of the most enigmatic aspects of modern science. Despite ongoing debates regarding its true nature, dark energy is often treated as a smooth and homogeneous energy field that pervades space. Its negative pressure drives the accelerated expansion of the cosmos, making it a crucial player in shaping the universe's fate. By incorporating dark energy into the equations that govern cosmology, scientists have been able to explain the relationship between the universe's expansion rate and its total mass energy content. This inclusion has led to predictions that align closely with empirical data derived from supernovae observations and the cosmic microwave background, CMB radiation. When paired with dark matter, this model paints a more complete picture of the universe's makeup and dynamics. Dark matter, although invisible, exerts a gravitational influence, helping to form galaxies, clusters, and the vast cosmic web we observe today. The gravitational effects of dark matter on the universe's large-scale structure are integral to understanding the distribution of galaxies and the geometry of space itself. The combination of dark energy and dark matter provides a framework that allows researchers to trace the universe's evolution from its early moments to its current state, and perhaps even predict its ultimate destiny. The LCDM model's explanatory power lies in its ability to account for a wide range of cosmic phenomena. One of its major successes is in explaining the flat geometry of the universe, a concept that has been supported by detailed observations of the CMB radiation. Furthermore, the model accurately predicts the temperature fluctuations detected in the CMB, providing robust evidence for its validity. Scientists have also used this model to estimate the relative contributions of different forms of matter in the universe, including dark matter, dark energy, and ordinary baryonic matter, offering a comprehensive overview of the universe's present-day composition. Central to the LCDM framework is the role of cold dark matter, which plays an essential part in the formation of cosmic structures. Unlike its hotter counterpart, hot dark matter, which moves at relativistic speeds and prevents the formation of large structures, cold dark matter moves slowly enough to clump together under the influence of gravity. This allows it to provide the necessary scaffolding for galaxies and clusters to form over time. Small density fluctuations seeded by quantum processes in the early universe grew progressively as a result of gravitational attraction. These fluctuations eventually led to the formation of galaxies, clusters, and the intricate cosmic web that characterizes the observable universe. Additionally, the LCDM model has become a cornerstone in the study of cosmic evolution. It helps explain not only the acceleration of the universe's expansion, but also the large-scale structure of the universe we see today. The model's ability to predict the distribution of galaxies and other cosmic phenomena has been tested and confirmed through various astronomical observations, further reinforcing its credibility. Scientists employ advanced supercomputers to simulate the early universe, particularly the first moments after the Big Bang, a period marked by extreme heat and density. Recreating these conditions in a laboratory setting is an immense challenge, but through detailed simulations, researchers can explore how matter and energy behave during this primordial phase. By running complex algorithms and equations of state, these supercomputers model the interactions of fundamental particles under the extreme conditions that prevailed at the universe's inception. These simulations help scientists investigate the formation of particles like quarks and electrons, and the subsequent creation of protons and neutrons. They also shed light on the rapid expansion phase known as cosmic inflation, a crucial period that explains how the universe transitioned from a hot, dense state to the cooler, more structured cosmos we observe today. Understanding this early phase of rapid expansion is key to unlocking the mysteries of the universe's formation and its ongoing evolution. As the LCDM model continues to guide cosmological research, it remains a vital tool for understanding the past, present, and future of the cosmos. Its ability to harmonize theoretical predictions with observational data ensures its place at the forefront of our exploration into the vast, unknown universe. Moreover, these supercomputers draw on vast amounts of data from particle physics experiments, such as those conducted at the Large Hadron Collider. By integrating this data with their simulations, scientists can test their models against real-world observations. This process deepens our understanding of the early universe and provides profound insights into the fundamental physical laws and forces that shape the reality we experience. The results from these simulations can even predict the universe's evolution, influencing our knowledge on topics like cosmic microwave background radiation, galaxy formation, and the mysterious dark matter. As technology continues to evolve, simulations are becoming more sophisticated, allowing scientists to peer even deeper into the moments immediately following the Big Bang, uncovering the very origins of everything we know. However, despite the remarkable capabilities of current cosmological simulations, they face several significant limitations. One of the biggest challenges is the complexity of the forces and particles involved in the universe's evolution. While simulations can effectively model large-scale structures and behaviors, they often struggle to accurately represent the intricacies of galaxy formation and the interactions that occur on smaller scales. This discrepancy can create a gap between simulated results and real observational data, especially when it comes to the distribution and behavior of dark matter. Another limitation arises from the sheer computational power needed for detailed simulations. Even with supercomputers, there are constraints on the resolution and size of the simulated volume. Most simulations can either achieve high resolution in a limited region or encompass a larger region with lower resolution. This trade-off means that some important phenomena, such as the processes of star formation or the dynamics of black holes, may not be captured in full detail. As a result, our understanding of how these processes influence the evolution of the universe remains limited. Additionally, our current understanding of fundamental physics and cosmological parameters is incomplete. For instance, the mysterious nature of dark energy and dark matter presents a substantial challenge. Most simulations rely on simplified models or assumptions about these elusive components, and without a comprehensive understanding of their true properties, predictions made by these simulations can often be uncertain or flawed. The human element also plays a role in these challenges. Many simulations involve choices about initial conditions, model parameters, and simplifications made by the researchers themselves. Different research teams may adopt varying assumptions, leading to discrepancies in the outcomes. To improve the reliability of cosmological simulations, collaboration among scientists and continuous advancements in observational techniques and theoretical physics are essential. Scientists validate and refine their cosmological models through a systematic process, comparing predictions from their simulations with real-world observations. They analyze data collected from both ground-based and space-based telescopes that capture images and spectral information from distant galaxies, cosmic microwave background radiation, and other astronomical phenomena. This empirical data becomes a crucial benchmark against which theoretical models are tested, helping scientists determine how well their simulations align with actual observations in the universe. Furthermore, scientists engage in the practice of peer review and collaborative research, sharing their findings with the global scientific community. Feedback from peers can reveal potential flaws in assumptions or methodologies, prompting further refinement. Working with a diverse range of researchers across various subfields allows for the integration of insights that enhance the accuracy and comprehensiveness of cosmological models. Results are often published in scientific journals, where they undergo rigorous scrutiny, fostering an environment of continuous improvement in cosmological theories. Refinement also happens through iterative modeling. As new data becomes available or existing data is reanalyzed, scientists revisit their models, adjusting parameters and recalibrating simulations to align better with the updated information. For example, improved measurements of galaxy distributions, cosmic expansion rates, or the properties of dark matter allow researchers to revise their models and significantly enhance the precision of predictions about the universe's behavior. In addition to these traditional methods, scientists are increasingly incorporating machine learning and artificial intelligence into their modeling processes. By training algorithms on vast data sets, researchers can identify patterns and correlations that might be missed by conventional techniques. This innovative approach has the potential to uncover new relationships and reveal previously unknown phenomena, enriching our understanding of the cosmos and leading to more refined theoretical frameworks. Artificial intelligence, AI, is playing an increasingly vital role in both creating and analyzing cosmological simulations, revolutionizing how scientists study the universe. One significant application of AI lies in data analysis. The vast amounts of data generated by astronomical observations and cosmological simulations can be overwhelming, but machine learning algorithms excel at processing these large data sets, identifying patterns and making connections that would be difficult, if not impossible, for humans to discern. For example, AI can help classify galaxies, analyze their shapes, and to predict their formation processes based on features extracted from the data. In the creation of simulations, AI also helps optimize model parameters in real time. Algorithms can examine different configurations and dynamically adjust them, leading to more efficient simulations. This capability allows researchers to explore a broader range of potential scenarios and outcomes in far less time than traditional methods would allow. By harnessing AI's capabilities, researchers can not only save time, but also enhance the accuracy and detail of their models, making them more representative of the true underlying physics at play. In sum, the fusion of observational data, collaborative research, technological advancements, and AI is transforming how cosmologists validate and refine their models. The process is evolving, enabling scientists to deepen our understanding of the universe in unprecedented ways, moving ever closer to unlocking the mysteries of our cosmos. Artificial intelligence, AI, is revolutionizing the field of cosmology, offering groundbreaking tools to interpret the vast and complex data generated by cosmological simulations. By integrating AI into this area of research, scientists can identify intricate relationships among various cosmological parameters and assess the consistency of simulated data with real-world observational data. AI's capacity to handle immense datasets, combined with advanced techniques like neural networks, allows researchers to build predictive models that not only analyze current phenomena, but also forecast future astronomical events. This symbiotic relationship between AI and cosmology is advancing our understanding of the universe's intricate systems and shedding light on its evolving nature and the fundamental forces that shape it. Moreover, AI facilitates collaboration among scientists by providing sophisticated data visualization tools that make complex concepts more accessible. Using AI-driven visualization techniques, researchers can create dynamic, interactive models and presentations that convey their findings with unprecedented clarity. This enhanced ability to represent data visually fosters greater collaboration and ensures that cosmological research reaches a broader audience, extending beyond the confines of the scientific community. In doing so, AI not only advances the field of cosmology, but also makes its discoveries more comprehensible and engaging to people from diverse backgrounds. The fusion of AI with cosmological simulation marks a paradigm shift in contemporary astrophysics, driving research into uncharted territories. Simulations, which serve as essential tools for understanding the universe's past, present, and future, enable scientists to model the complexities of cosmic structures and their interactions. By incorporating fundamental physical laws such as gravity and thermodynamics, these simulations offer insights into how the universe's components evolve and how different forces interact to shape its destiny. One of the most significant contributions of cosmological simulations is their ability to predict the universe's future. By experimenting with various initial conditions and parameters, researchers can observe potential outcomes and better understand the universe's long-term development. This includes modeling cosmic phenomena such as galaxy formation, star evolution, and the ongoing dynamics of dark matter. By studying the universe's history through simulations, scientists can identify patterns that suggest how the cosmos might continue to evolve. For example, simulations can demonstrate how galaxies might merge over billions of years, how star formation rates could fluctuate, or how dark matter's gravitational influence might alter the fabric of the cosmos. Understanding the role of dark energy, which is currently driving the accelerated expansion of the universe, is another crucial area where AI-enhanced simulations are playing a pivotal role. Researchers use these simulations to manipulate different models of dark energy, exploring its potential characteristics and how its influence might change over time. This, in turn, helps scientists predict the universe's eventual fate, whether it will continue expanding indefinitely, reach a stable equilibrium, or eventually collapse. By providing these insights, AI-powered simulations allow researchers to ask and answer some of the most fundamental questions about the cosmos's long-term trajectory. Simulations also enable the study of specific cosmic events, like supernova or black hole interactions, that could have profound effects on the universe's evolution. By analyzing these phenomena within simulated environments, scientists can refine their models and predictions, leading to more accurate forecasts of how such events might impact surrounding matter and energy. These models not only deepen our understanding of past cosmic events, but also help scientists make informed predictions about future occurrences, strengthening our overall grasp of the universe. Cosmological simulations have already led to a number of revolutionary discoveries that have fundamentally changed how we view the universe. One of the most unexpected revelations from early simulations was the discovery of the cosmic web, a vast, interconnected network of galaxies bound together by filaments of dark matter and gas. This intricate structure defies our intuitive understanding of how matter organizes itself on such grand scales. The identification of the cosmic web has underscored the importance of dark matter in shaping the universe's large-scale structure, even though this mysterious substance remains largely invisible and poorly understood. Another surprising finding from these simulations concerns the role of feedback processes in galaxy formation. Before these simulations, scientists believed that gas would simply collapse under gravity to form galaxies. However, simulations revealed that energetic phenomena such as supernova explosions and the activity of supermassive black holes within galactic centers play a critical role in shaping the formation of stars. These feedback mechanisms can expel gas from galaxies, regulate star formation rates, and even stimulate the birth of new stars. This revelation forced scientists to reconsider their models of galaxy evolution, highlighting the complexity and dynamism of the processes that govern the birth and life of galaxies. Simulations have also challenged long-standing assumptions about dark energy. Early models suggested that dark energy's effects on the universe would be relatively uniform throughout space. However, as simulations have become more refined, they have provided new insights into the complex nature of dark energy, suggesting that its influence may vary across different regions of the universe. This discovery has profound implications for our understanding of the universe's expansion, particularly as it relates to the ultimate fate of cosmic structures. Through these insights and more, AI-powered cosmological simulations are not only reshaping our understanding of the universe's past, but also providing powerful tools to predict its future. By continuously refining these simulations, scientists are breaking new ground in our quest to understand the cosmos, helping to answer fundamental questions about the nature of dark matter, dark energy, and the cosmic processes that shape the fabric of reality itself. In doing so, they are uncovering the mysteries of the universe, one simulation at a time. However, sophisticated models have uncovered a surprising revelation. The distribution of dark energy may not be uniform throughout the universe. Instead, it could vary, creating regions where the rate of cosmic expansion is vastly different. This finding raises profound questions about the true nature of dark energy and its role in determining the ultimate fate of the universe. As our understanding of this mysterious force deepens, these insights from advanced simulations are sparking new lines of inquiry, pushing astronomers and physicists to rethink what we thought we knew about the cosmos. Furthermore, simulations have pointed toward another unexpected discovery: the existence of rogue planets, celestial bodies that do not orbit a star but instead drift freely through the galaxy. This concept dramatically shifts our understanding of planetary systems and their dynamics. Researchers have found that through gravitational interactions and collisions with other celestial bodies, planets can be ejected from their original orbits, hurled into interstellar space. This discovery not only challenges our perceptions of what constitutes a planetary system, but also suggests that our solar system may not be as typical as we once believed. It opens a new chapter for exploration, inviting deeper questions about how planets form, exist, and wander through the vastness of space. Each of these findings underscores the immense power of cosmological simulations, which continue to reveal the universe's complex and often surprising nature. These simulations help us challenge long-held assumptions and explore the intricate web of forces that govern the cosmos. Meanwhile, astronomers turn their gaze to the oldest light in the universe, the cosmic microwave background, CMB, radiation. This faint afterglow of the Big Bang offers a direct glimpse into the universe's infancy, dating back roughly 380,000 years after the event when atoms first formed and photons were free to travel across space. The detection of this ancient light has become a cornerstone of cosmological research, offering profound insights into the early universe's structure, composition, and evolution. To capture the CMB, astronomers rely on specialized instruments designed to detect microwave wavelengths, often positioned in space to avoid interference from Earth's atmosphere. Notable missions, such as the Wilkinson Microwave Anisotropy Probe, WMAP, have mapped temperature variations across the sky, uncovering tiny fluctuations in the intensity of the CMB. Later, the Planck satellite provided even more detailed measurements, allowing scientists to refine their understanding of the universe's age, shape, and composition. These observations have confirmed key aspects of modern cosmology, such as the flatness of the universe and the existence of dark matter and dark energy. Through meticulous analysis of the CMB, scientists have gathered a wealth of data that informs our understanding of the universe's large-scale structure and the processes that have shaped its evolution over billions of years. Each discovery helps to weave together the complex history of our universe, providing a clearer picture of how it expanded and developed into what we observe today. In another groundbreaking achievement, the Laser Interferometer Gravitational Wave Observatory, LIGO, has become a game-changer in the study of space-time. LIGO is designed to detect gravitational waves, ripples in the fabric of space-time caused by some of the most violent and energetic processes in the universe, such as the collision of black holes or neutron stars. With two observatories located in Washington and Louisiana, LIGO measures minute shifts in the distance between suspended mirrors to pinpoint the source of these waves. LIGO's contributions go far beyond merely detecting these cosmic ripples. Gravitational waves carry crucial information about their origins. By analyzing the waves, scientists can gain insights into the masses, spins, and other properties of objects involved in such extreme events. This data significantly enriches our understanding of stellar evolution, the behavior of matter under extreme conditions, and the fundamental laws that govern the universe. While LIGO predominantly detects current cosmic phenomena, its implications stretch back to the very early universe. Gravitational waves are thought to have been produced during the universe's infancy, especially during a period known as cosmic inflation, a rapid expansion that took place shortly after the Big Bang. By studying these waves, scientists hope to uncover crucial information about the conditions of the early universe, the nature of inflationary processes, and the formation of primordial structures. Together, these discoveries are not only reshaping our understanding of the universe, but also opening up new avenues of exploration. Each new insight builds upon the last, revealing a more intricate and interconnected cosmos than we ever imagined. Moreover, the groundbreaking discoveries made by LIGO have opened the door to an entirely new field of study: gravitational wave astronomy. This emerging discipline promises to revolutionize how we explore the cosmos, offering a multi-messenger approach to understanding the universe. By combining the data collected from gravitational waves with electromagnetic observations from traditional telescopes, scientists are gaining an unprecedented, holistic view of cosmic events. Together, these methods weave a richer, more intricate tapestry of the universe, providing deeper insight into the fundamental processes that have shaped it, from the cataclysmic birth of the cosmos to the present day. As LIGO continues its mission and new facilities come online, the wealth of information gathered will undoubtedly sharpen and refine our understanding of the universe's history, as well as the underlying physical principles that govern its existence. Each discovery will not only enhance our knowledge, but also challenge and expand our conceptual framework of the universe itself. In tandem with these gravitational wave observations, space telescopes like the James Webb Space Telescope, JWST, are playing an indispensable role in unveiling the universe's past. JWST allows astronomers to peer deeper into space and further back in time, by capturing light that has traveled across vast stretches of the cosmos. When we look at distant galaxies or stars, we are not simply observing them as they appear in the present. Instead, we are seeing them as they were billions of years ago, at the very moment their light first left them. This ability to observe the distant past provides a unique glimpse into the evolution of the universe. As light journeys across the expanding universe, it undergoes a phenomenon called redshift, where the wavelength of the light is stretched due to the expansion of space. This effect causes the light to shift toward the red end of the electromagnetic spectrum, making it appear more infrared. Many of the earliest stars and galaxies were formed during a period known as the cosmic dawn, which occurred shortly after the Big Bang. The light from these distant, ancient objects has been redshifted beyond the visible spectrum, and it is best captured in the infrared range. Here, the James Webb Space Telescope shines. Equipped with advanced instruments capable of detecting infrared radiation, JWST can collect this light, unveiling details about these ancient cosmic structures that were once hidden from our view. By analyzing this light, scientists can uncover a wealth of information, such as the composition and temperature of these early celestial bodies, as well as their formation and evolutionary history. For example, JWST can reveal how galaxies merged and evolved, ultimately leading to the complex cosmic structures we observe today. In doing so, it creates a timeline of the universe, shedding light on pivotal moments in its history. Moreover, the study of light from distant stars helps to reveal the processes behind the formation of elements, providing critical insights into the conditions of the early universe. By measuring the light from ancient celestial bodies, JWST can uncover the processes that led to the synthesis of elements after the Big Bang, further enriching our understanding of stellar and galactic formation. In essence, the James Webb Space Telescope acts as a cosmic time machine. By peering into the past, it opens a window to understanding not only the universe's history, but also the forces that continue to shape its present and future. Redshift itself is a key phenomenon in modern cosmology. It occurs when the light emitted by an object in space is stretched to longer wavelengths as it travels across the expanding universe. When an object, such as a galaxy, moves away from us, the light waves it produces are stretched, shifting the light toward the red end of the electromagnetic spectrum. This is the essence of redshift, an indicator of motion and a clue to the universe's ongoing expansion. To understand redshift, think of the sound of a train passing by. As the train moves away, the sound becomes lower in pitch. Similarly, as light travels across the universe, particularly from distant galaxies, its wavelength is stretched, causing a shift toward the red end of the spectrum. This is not merely a marker of motion. Redshift is one of the most powerful tools astronomers have to study the universe's expansion. In fact, redshift holds the key to understanding how fast galaxies are moving away from us. By measuring the amount of redshift in the light emitted by distant galaxies, scientists can calculate the speed at which those galaxies are receding. This information is critical for unraveling the dynamics of cosmic expansion, and it allows astronomers to map out the growth and evolution of the universe. The groundbreaking work of Edwin Hubble in the early 20th century provided strong evidence for an expanding universe, based on his observations of redshift in the light from distant galaxies. His discovery laid the foundation for modern cosmology, and the study of redshift has continued to be essential in our quest to understand the cosmos. In addition to revealing the expansion of the universe, redshift is also crucial for estimating the age of the universe itself. Light emitted by galaxies has traveled across vast distances over billions of years, carrying with it a record of its journey through time and space. By analyzing the light from these ancient galaxies, scientists can estimate how long it has taken for the light to reach us and at what epoch that light was first emitted. The greater the redshift, the further away and consequently the older the galaxy is. This allows astronomers to construct a timeline of cosmic history, offering a glimpse into the universe's earliest moments and providing vital clues about the processes that led to the universe as we know it today. Furthermore, redshift plays a vital role in helping us understand the effects of dark energy, a mysterious force that is driving the accelerated expansion of the universe. By examining the redshift of light from distant galaxies, scientists can uncover how the universe's rate of expansion has evolved over time. This insight into the cosmic past is not only key to refining our understanding of when the universe began to expand, but it also contributes to unraveling the intricate interplay of forces that will shape its future. Through the lens of redshift, we begin to grasp the very fabric of the universe's evolution, tracing the expansive journey it has taken across vast epochs of time. But this is just one piece of the cosmic puzzle. To further understand the forces that have shaped the universe, scientists also focus on detecting and studying primordial gravitational waves, ripples in space-time that originated from events in the early universe, particularly during cosmic inflation. Gravitational waves are faint disturbances, so weak that they can be easily masked by the noise from more recent astrophysical events. The challenge, then, lies in isolating these primordial signals from the surrounding cosmic background. To achieve this, researchers rely on cutting-edge technologies, including gravitational wave observatories and experiments designed to study the cosmic microwave background, CMB, the afterglow of the Big Bang itself. In particular, observatories like the Laser Interferometer Gravitational Wave Observatory, LIGO, and the upcoming LIGO Australia, alongside space-based instruments such as the Laser Interferometer Space Antenna, LISA, are crucial to detecting the faint distortions in spacetime caused by passing gravitational waves. While LIGO has focused on detecting signals from more recent events like black hole mergers, future missions are poised to pinpoint waves that are linked to primordial cosmic events. These upcoming missions will require extreme sensitivity and precision, covering broader frequency ranges to capture these subtle signals. A complementary approach involves studying the cosmic microwave background. As the radiation from the Big Bang travels through space, it carries imprints of ancient events, including the presence of primordial gravitational waves. These waves stretch and compress space during cosmic inflation, leaving distinct patterns in the polarization of the CMB, specifically through a phenomenon known as B-modes. By analyzing these patterns with advanced telescopes like the upcoming Simon Observatory and the already operational Planck satellite, scientists can infer the presence and characteristics of these primordial waves. Moreover, theoretical models of cosmic inflation predict specific signatures and patterns of gravitational waves, helping to shape the way scientists interpret their findings. By comparing observational data with these models, researchers can refine our understanding of different inflationary scenarios and better measure key cosmological parameters. The precision of these measurements not only illuminates the conditions of the early universe, but also offers profound insights into fundamental physics and the mechanisms that govern the universe's initial moments. Through these ongoing efforts, scientists continue to unravel the mysteries of the universe's formative stages. This exploration holds the potential to reshape our understanding of gravitational waves and the very nature of spacetime itself, offering new perspectives on the evolution of cosmic structures. Meanwhile, in the world of particle physics, the Large Hadron Collider, LHC, the largest and most powerful particle accelerator on Earth, stands as a beacon of scientific discovery. Located at CERN, the European Organization for Nuclear Research near Geneva, Switzerland, the LHC spans an impressive 17 miles in circumference. It accelerates protons and heavy ions to nearly the speed of light before colliding them, recreating the high-energy conditions that existed shortly after the Big Bang, albeit on a much smaller scale. The LHC plays an essential role in addressing fundamental questions about the universe and the nature of matter. By pushing the boundaries of particle physics, it provides invaluable insights into the building blocks of the cosmos and the fundamental forces that govern its behavior. Through its experiments, the LHC continues to explore some of the most profound mysteries of the universe, deepening our understanding of how everything, from the smallest particles to the largest cosmic structures, fits together. One of the primary goals of the Large Hadron Collider, LHC, is to investigate the fundamental building blocks of matter, as described by the Standard Model of particle physics. When protons collide at extremely high energies, they create a cascade of particles, some of which may have existed only in the earliest moments of the universe. By analyzing the particles produced in these collisions, scientists can uncover valuable insights into the conditions that prevailed right after the Big Bang, including temperature, density, and the formation of the fundamental forces. The LHC has already made groundbreaking contributions to our understanding of the early universe. One of the most significant achievements came in 2012 with the discovery of the Higgs boson. This elusive particle plays a pivotal role in explaining how other particles acquire mass, and its discovery confirmed key theoretical predictions. It also provided vital insight into the mechanisms that shaped the universe shortly after the Big Bang. By recreating the extreme conditions of those early moments, the LHC enables scientists to test hypotheses about the primordial states of matter and the forces that govern the universe's evolution. In the high-energy environment created by the LHC collision, scientists can study particles under conditions similar as present during the universe's infancy. This helps them test theories about the formation of matter, the nature of dark matter, and the early behavior of fundamental forces. Furthermore, the LHC opens a window into the study of quark-gluon plasma, a unique state of matter that existed just microseconds after the Big Bang. In this state, quarks and gluons, which are the building blocks of protons and neutrons, exist independently rather than bound together. By recreating these conditions, scientists can explore how the universe transitioned from a hot, dense soup of quarks and gluons to the hadrons that make up protons and neutrons. As the universe cooled and expanded, fundamental changes took place. The insights gained from the LHC experiments are deepening our understanding of the forces at play during the early universe. These findings not only enrich our knowledge of particle physics, but also inform broader cosmological theories, linking the study of the smallest scales of matter to the vastness of the cosmos. Neutrinos, the elusive and nearly massless particles produced in some of the most extreme events in the universe, play a crucial role in expanding our understanding of the early universe. Though abundant, neutrinos interact very weakly with matter, making them incredibly difficult to detect. Nevertheless, they offer a unique perspective on the conditions immediately following the Big Bang, particularly during nucleosynthesis, the process by which the lightest elements like hydrogen, helium, and lithium were formed. In the early universe, neutrinos were produced in vast quantities as the universe cooled and underwent major transformations. These primordial neutrinos are believed to permeate the cosmos today, forming a cosmic background similar to the cosmic microwave background, CMB radiation. Although these relic neutrinos are too faint to detect directly, experiments like the IceCube Neutrino Observatory and Super Kamiokande have been pivotal in capturing high-energy neutrinos produced by modern astrophysical phenomena. This provides scientists with a glimpse into the processes that occurred in the universe's infancy. When supernovae explode, they generate a torrent of neutrinos in a brief but intense pulse. These neutrinos can escape the stellar collapse, traveling across vast expanses of space without being absorbed. By studying supernova neutrinos, scientists gain crucial insights into the dynamics of these explosive events and the nuclear reactions taking place within the core of the collapsing star. This information helps us understand stellar evolution and the conditions in which elements were formed, key components in understanding the early universe. Additionally, neutrino detectors help refine our understanding of nucleosynthesis, the process responsible for the creation of light elements in the hot, early universe. The interactions of neutrinos during this era may have influenced the rates of nuclear reactions, affecting the final abundances of hydrogen, helium, and lithium. By examining neutrino interactions, researchers can improve theoretical models of nucleosynthesis, bringing us closer to understanding how the elements we observe in the universe today were forged. The study of neutrinos intersects with many fields, including particle physics, cosmology, and astrophysics. By enhancing our knowledge of these particles, researchers can test and refine existing cosmological models, contributing to our understanding of the universe's origins and the fundamental forces that govern its behavior. As technology and neutrino detection methods continue to evolve, the potential for groundbreaking discoveries in this field remains immense, promising even deeper insights into the universe's mysteries. One such initiative pushing the boundaries of neutrino research is the Deep Underground Neutrino Experiment, DUNE. An ambitious international collaboration, DUNE is located deep underground at the Sanford Underground Research Facility in South Dakota. It will study neutrinos produced by powerful particle collisions at Fermilab in Illinois. The goal of Dune is to investigate phenomena such as neutrino oscillation, the process by which neutrinos change flavor as they travel. This phenomenon holds the key to understanding the mass of neutrinos and their intrinsic properties. By measuring neutrino oscillations with high precision, Dune hopes to uncover critical information about the differences in mass between the three types of neutrinos. This knowledge could also shed light on the long-standing mystery of the matter-antimatter asymmetry in the universe, the apparent imbalance between matter and antimatter, which remains one of the greatest unsolved problems in cosmology. The study of neutrinos offers a unique opportunity to explore the very nature of matter, energy, and the fundamental forces that have shaped the evolution of the universe. Through Dune and other experiments, scientists are on the cusp of uncovering new truths about the origins of the universe, the particles that compose it, and the forces that govern its behavior. The future of neutrino research holds the promise of deepening our understanding of the universe in ways that are still unimaginable, pushing the boundaries of both science and human knowledge. When a massive star explodes as a supernova, it triggers a cosmic event that sends a burst of neutrinos cascading through space. These elusive particles, often referred to as ghost particles, provide a wealth of information about the internal processes of the explosion. By studying these neutrinos, scientists can unlock unprecedented insights into the dynamics of supernova, shedding light on how these cataclysmic events occur, and more importantly, the role they play in the creation of elements. The study of supernova neutrinos also promises to offer valuable clues about how such cosmic events influence the very evolution of the universe itself. This is where Dan's experiment comes into play. It aims to enhance our ability to detect neutrinos from both artificial sources and future supernovae within our galaxy. By doing so, scientists will be able to collect data that could significantly expand our understanding of pivotal cosmic events. Furthermore, Dan's work is not limited to just the study of supernovae. The experiment also seeks to explore the potential connections between neutrinos and dark matter. Neutrinos are already known to be elusive, but their rare interactions could hint at new physics beyond the standard model of particle physics, offering crucial insights into the unknown nature of dark matter and the composition of the universe. By advancing our knowledge of neutrinos and their properties, the experiment holds the potential to change the way we think about both the universe's origin and its ongoing evolution. In the world of fundamental physics and cosmology, understanding these particles could offer groundbreaking revelations that alter the trajectory of scientific inquiry for decades to come. While neutrinos offer profound insights, quasars also play an indispensable role in our understanding of the cosmos, especially when it comes to studying the early universe. These incredibly bright, quasi-stellar objects are powered by supermassive black holes at the centers of distant galaxies. As matter falls into these black holes, it accelerates and heats up, emitting vast amounts of radiation that can outshine entire galaxies. This immense luminosity allows scientists to study quasars even at distances of billions of light years by offering a rare glimpse into the conditions of the universe at various stages of its evolution. One of the most remarkable ways quasars help astronomers probe the early universe is through the light they emit. As this light travels across vast cosmic distances, it passes through space filled with gas and dust. The information contained in this light provides scientists with an invaluable record of the chemical composition, temperature, and density of the intergalactic medium, revealing conditions that existed billions of years ago, near the epoch of reionization that followed the Big Bang. In addition to shedding light on the universe's composition, quasars also serve as powerful tools for studying cosmic evolution. Their extreme brightness enables astronomers to observe them as they appeared in the distant past, essentially allowing them to look back in time. By examining quasars from different epochs, researchers can trace the formation and evolution of galaxies and supermassive black holes, tracking how these celestial bodies and structures grew over cosmic history. Furthermore, by monitoring how quasar properties change over time, scientists can study shifts in star formation rates and black hole growth, providing essential context for understanding the universe's larger evolution. Quasar feedback is another crucial phenomenon that astronomers investigate. As supermassive black holes consume surrounding material, they often release energy in the form of powerful jets and winds. These high-energy emissions can have profound effects on the galaxies that host the black holes, influencing star formation rates and regulating galaxy growth. This feedback mechanism offers key insights into how galaxies, including our own, have been shaped over time. The interplay between quasars and their host galaxies provides a window into the forces that govern the large-scale structure of the universe. With ongoing advancements in observational techniques and the development of next-generation telescopes, the study of quasars is poised to offer even deeper insights into the early universe. These cosmic beacons provide a unique and multifaceted view of the cosmos, illuminating both its composition and its evolution. The information gleaned from quasar observations not only enhances our understanding of the universe's history, but also paves the way for new discoveries that could redefine our place in the cosmos. As we look to the future, several groundbreaking technologies are on the horizon that promise to revolutionize our understanding of the universe's origins. One of the most exciting developments is the advent of next-generation space telescopes. The James Webb Space Telescope has already begun to transform our view of the cosmos, offering unprecedented detail on distant galaxies and stars. Future telescopes targeting different wavelengths such as gravitational waves and various parts of the electromagnetic spectrum will complement Webb's findings, helping scientists probe the earliest moments of the universe's formation. At the same time, cutting-edge detectors for neutrinos and dark matter are being developed. Neutrinos, due to their elusive nature, have long been a mystery in the field of particle physics. These particles interact with matter so rarely that they can travel through entire planets without being detected. As scientists refine their ability to detect these ghostly particles, they hope to uncover clues about the fundamental forces that govern the universe. Dark matter, which makes up a significant portion of the universe's mass, yet remains invisible to our current instruments, could also be revealed through these advancements, leading to new breakthroughs in our understanding of the universe's true composition. Together, these technologies represent the cutting edge of cosmological research, providing scientists with the tools they need to unravel the deepest mysteries of the universe. From the study of neutrinos to the exploration of distant quasars, the future of astrophysics holds immense promise, offering the potential for discoveries that could reshape our understanding of the cosmos for generations to come. However, they can offer crucial insights into the most profound cosmic phenomena, like supernovae and the intricate processes occurring deep within the cores of stars. With the advent of advanced neutrino observatories, scientists are now able to detect these elusive particles with unprecedented accuracy, potentially unlocking secrets about the universe's conditions shortly after the Big Bang. These neutrino emissions, often regarded as the silent messengers of the cosmos, could shed light on the forces that shaped the early universe in ways that were previously unimaginable. Meanwhile, quantum computing is making remarkable strides in the field of astrophysics. The ability to process vast amounts of data, from complex simulations to massive observational datasets, at speeds that far exceed traditional computers, is revolutionizing our understanding of the cosmos. Quantum systems are enabling researchers to model highly intricate astrophysical processes that were once too complex to simulate. By harnessing this extraordinary computational power, scientists are now able to simulate entire galaxies or sift through enormous data sets from large-scale sky surveys. This progress is bringing us closer to confirming long-standing theories about the birth and evolution of our universe. In parallel, planetary exploration technologies are poised to play an instrumental role in our quest to understand the origins of life and the history of our solar system. Missions targeting Mars, Europa, and other distant celestial bodies hold the promise of unearthing clues about the fundamental building blocks of life. By studying the geology and atmospheres of these worlds, coupled with data collected from various exploratory missions, we can begin to piece together not only the story of Earth, but of the entire universe. Each of these groundbreaking technologies contributes a critical piece to the ever-expanding puzzle, helping to illuminate the mysteries surrounding the cosmic dawn. One of the most captivating theories emerging from these advancements is the concept of cosmic inflation, a rapid expansion of the universe that occurred during the first moments after the Big Bang. According to this theory, the universe underwent an exponential expansion in the briefest fraction of a second, growing from an infinitesimally small point to its vast size today. This phenomenon, which occurred in the first moments following the Big Bang, provides a compelling explanation for several perplexing observations in cosmology, including the uniformity of the cosmic microwave background radiation and the large-scale structure of the universe. Put simply, the theory of inflation suggests that the universe began as an incredibly tiny and dense point, but within an extraordinarily brief period, it expanded at an unimaginable rate. This rapid expansion smoothed out the distribution of energy and laid the groundwork for the formation of galaxies and stars. The theory was first proposed in the early 1980s by renowned cosmologist Alan Guth, whose pioneering work suggested that in the early moments of the universe, space expanded far faster than the speed of light due to a dominant high-energy field. This concept offered a novel explanation for the isotropy and homogeneity observed in the cosmos, resolving major issues such as the flatness problem, which relates to the curvature of space itself. Following Guth's groundbreaking work, other leading physicists such as Andre Linde and Paul Steinhardt further refined and expanded upon the inflationary model, contributing new variations and mechanisms that could drive inflation. These contributions have transformed the theory into a comprehensive framework for understanding the universe's earliest moments. Importantly, the theory suggests that inflation may still be occurring today, albeit at a much slower pace, offering a tantalizing glimpse into the ongoing evolution of the cosmos. Understanding cosmic inflation not only helps astronomers piece together the universe's history, but also elegantly addresses some of the most profound questions regarding its structure and evolution. Inflation provides solutions to two critical challenges in our understanding of the universe: the horizon problem and the flatness problem. The horizon problem stems from the observation that distant regions of the universe, separated by vast distances, show remarkably similar properties, despite not having had enough time to influence each other. For example, the cosmic microwave background radiation exhibits an astonishingly uniform temperature, even across regions of the universe that are causally disconnected. Inflation theory suggests that all regions of the universe were once in close proximity, allowing them to interact and reach thermal equilibrium before the rapid expansion took place. This expansion stretched these regions far apart, preserving their uniformity despite the vast distances that now separate them. The flatness problem, on the other hand, addresses the question of why the universe appears so spatially flat. According to general relativity, the density of the universe determines its curvature. A dense universe would curve inward like a sphere, while a sparse one would curve outward like a saddle. Observations show that the universe has a density so close to what is required for flatness that it appears almost perfectly flat. Cosmic inflation proposes that in the moments following the Big Bang, the universe's exponential expansion smoothed out any initial curvature, creating a cosmos that appears flat. This is analogous to how a small section of a balloon appears flat, even though the entire surface is curved. Through the lens of inflationary theory, space itself was stretched to such an extent that any initial density irregularities were smoothed out, leading to the observed flat geometry of the universe we see today. This elegant solution not only reshapes our understanding of the universe's beginnings, but also holds the key to unlocking deeper mysteries that have puzzled scientists for generations. Furthermore, inflation theory suggests that shortly after the universe began to cool and expand, quantum fluctuations, those minute, unpredictable deviations in energy, began to take shape. These fluctuations, which were present during the universe's rapid inflationary phase, could have played a crucial role in seeding the large-scale structures we observe in the cosmos today. As inflation ended, these quantum fluctuations were magnified, creating density variations that eventually gave rise to galaxies, clusters, and other cosmic structures. In this way, Cosmic inflation not only resolves some of the universe's greatest mysteries, like the horizon and flatness problems, but also provides a plausible mechanism for the formation of the universe's structure. The significance of cosmic inflation stretches far beyond the confines of theoretical physics. It serves as a unifying force, bringing together disparate observations and models into a coherent framework. This enables scientists to better understand the dynamics of the early universe and the fundamental principles that have shaped its evolution over billions of years. The weight of evidence supporting cosmic inflation has grown steadily, providing a more complete understanding of the universe's earliest moments. One of the most compelling pieces of evidence for inflation comes from the cosmic microwave background radiation, CMB, often referred to as the afterglow of the Big Bang. Precise measurements made by satellites such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck spacecraft have revealed tiny fluctuations in temperature across the sky. These fluctuations match the predictions made by inflationary models with remarkable accuracy, suggesting that quantum fluctuations during inflation played a vital role in shaping the universe's large-scale structures. This discovery not only bolsters the theory of inflation, but also ties it directly to observable phenomena. In addition to temperature variations, another key aspect of the evidence supporting inflation is the uniformity of the cosmic microwave background. According to inflationary theory, the entire universe was once in close proximity, allowing different regions to interact thermally. This would explain why large regions of space, separated by distances so vast that light could not travel between them since the beginning of time, exhibit nearly identical temperatures. This temperature uniformity aligns perfectly with the idea that these distant regions underwent a brief but intense period of rapid inflation. This stands in stark contrast to the classical Big Bang model, which struggles to explain such uniformity without invoking inflationary processes. Furthermore, observations of the large-scale structure of the universe provide another layer of evidence for inflation. Deep sky surveys have shown that galaxies are not randomly distributed across the universe, but instead form large-scale structures such as superclusters and vast cosmic voids. These patterns of distribution can be traced back to the small initial fluctuations predicted by inflation. Over billions of years, these tiny density variations were amplified by gravitational forces, eventually giving rise to the galaxies and clusters we see today. The remarkable correlation between these structures and the predictions of inflationary models adds significant credibility to the theory. The discovery of primordial gravitational waves, ripples in the fabric of space-time, could provide transformative evidence in support of cosmic inflation. These waves, potentially generated by the rapid expansion of the universe in its infancy, remain elusive, but experiments and observatories are actively searching for them. Should these waves be detected, they would provide direct confirmation of inflation, linking the theory even more firmly to the fundamental processes that shape the early universe. As technology advances and research continues, the possibility of uncovering further evidence for cosmic inflation remains an exciting prospect. In the realm of cosmology, inflation has far-reaching implications, especially when it comes to the concept of the multiverse, a hypothesis that suggests our universe may be just one of many, each governed by its own unique set of laws and properties. Cosmic inflation opens up the possibility that different regions of space could undergo inflation at different rates or under different conditions, leading to the creation of separate universes. This is the essence of the multiverse theory, a vast landscape of universes, each with its own distinct characteristics. One intriguing aspect of this theory is known as eternal inflation. According to this idea, inflationary processes could continue indefinitely in certain regions of space, creating pocket or bubble universes. Some of these regions would stop inflating and evolve into distinct universes with their own physical laws, while others would continue to inflate, generating an infinite array of new bubbles. Each bubble could develop its own set of rules, forces, and even types of matter, leading to a nearly endless variety of universes. The connection between inflation and the multiverse also sheds light on the so-called fine-tuning of our universe. In a multiverse scenario, the vast number of possible universes increases the chances that one would emerge with the precise conditions necessary for life. Instead of suggesting that our universe's characteristics were deliberately fine-tuned by an intelligent designer, the multiverse theory provides a more probabilistic interpretation. In this framework, our universe simply represents one of the many possible bubbles that happen to meet the right criteria for life to arise. In this sense, the astonishingly specific characteristics of our universe, those that allow life to flourish, could be seen as a natural consequence of the enormous variety of outcomes produced by eternal inflation. However, the multiverse theory remains a topic of intense debate within the scientific community. While the concept of inflation provides a captivating framework for understanding the universe's origins and structure, direct evidence supporting the existence of other universes remains out of reach. The very theoretical nature of the multiverse presents significant challenges in terms of empirical verification, making it a fascinating yet controversial idea in contemporary cosmology. As research continues, the connection between cosmic inflation and the multiverse is likely to remain a compelling and highly debated subject, pushing the boundaries of our quest to understand the cosmos. At the heart of the inflationary model lies a theoretical construct known as the inflaton field, which is proposed to explain the rapid expansion of the universe during its earliest moments. This field is imagined to permeate all of space, driving the rapid inflationary phase that occurred shortly after the Big Bang. The inflaton field is associated with a hypothetical particle, also called the inflaton, which carries the energy necessary to fuel the universe's explosive growth. During inflation, the inflaton field plays a crucial role in the energy density landscape, creating the conditions necessary for the universe to expand exponentially. In this state, the energy stored in the inflaton field behaves unlike typical matter or radiation. Instead of converting into particles or emitting energy in the form of light and heat, the inflaton field maintains a high energy state. This unique form of energy exerts a repulsive force that pushes space apart, accelerating the universe's expansion at an astonishing rate. The expansion can be likened to the inflaton field, exerting immense pressure that drives space itself to stretch, causing the universe to grow exponentially in a fraction of a second. As the universe continues to expand, however, the inflaton field gradually begins to lose its energy, transitioning from a high energy state to a lower energy configuration. This process, known as reheating, marks the end of inflation. During reheating, the energy stored in the inflaton decays into other particles, reintroducing matter and radiation into the universe. This transition sets the stage for the hot, dense conditions that characterize the early universe, leading to the formation of stars, galaxies, and other cosmic structures. Despite extensive theoretical development, the exact nature of the inflaton field, including how it interacts with other forces and fields, remains an ongoing area of research. Numerous models of inflation propose different types of inflaton fields, each with distinct characteristics. Finding experimental evidence or observable signatures tied to the inflaton field would provide a significant boost to the inflationary paradigm, helping us better understand the universe's origins. The search to unravel the mysteries of the inflaton is a key pursuit in cosmology, bridging the gap between theoretical physics, particle physics, and our understanding of the fundamental fabric of reality. Central to the inflationary model is its ability to explain the uniformity of the cosmic microwave background radiation, the faint glow left over from the Big Bang. This radiation is incredibly isotropic, meaning that it displays nearly identical temperatures across the sky, with only minuscule fluctuations. Yet, understanding how regions of the universe that are now separated by vast distances could have achieved such uniform conditions remains one of the greatest challenges in cosmology, especially when considering that these regions have never interacted since the Big Bang. The inflationary theory provides an answer to this dilemma by suggesting that the universe underwent a rapid phase of expansion shortly after the Big Bang. During this brief period, all regions of space that are now far apart were initially in close proximity, allowing them to exchange energy and thermal information. As the inflationary expansion took hold, these regions were stretched apart at speeds exceeding the speed of light, effectively separating them faster than they could influence one another. As a result, areas that are now causally disconnected once shared a common thermal equilibrium, leading to a uniform temperature across the sky. This sudden stretching smoothed out any initial irregularities in the density and temperature of the universe, a process that directly influenced the cosmic microwave background. Furthermore, as the universe continued to expand exponentially, tiny quantum fluctuations present during inflation laid the groundwork for structure formation in the cosmos. These fluctuations became the seeds for the vast and intricate cosmic structures we observe today, including galaxies, clusters, and vast cosmic voids. In this way, cosmic inflation not only offers a solution to the uniformity of the universe, but also provides the foundational framework for the growth of cosmic structures. Understanding the intricate details of inflation and its impact on the universe's evolution will continue to drive research and inspire new theories about the very nature of reality itself. Cosmic inflation, a pivotal concept in modern cosmology, is not just a theory, but a framework that connects the very early moments of the universe to the large-scale structures we observe today. While inflation played a crucial role in ensuring the uniformity of the cosmos by allowing regions to exchange information, the subtle fluctuations that arose during this period have far-reaching consequences. These tiny variations are significant for understanding the later formation of galaxies, stars, and the intricate web of cosmic structures that populate the universe. This rapid expansion of the universe provides an explanation for how the cosmos can appear homogeneous and isotropic despite its vastness. At the same time, it also offers a way to understand the small anisotropies present in the cosmic microwave background, the faint radiation left over from the Big Bang. These fluctuations, though minuscule, carry important clues about the early universe, serving as a bridge between the violent expansion that occurred just after the Big Bang and the galaxies and clusters of galaxies that exist today. The delicate interplay between this early burst of inflation and the quantum processes at play forms a cornerstone of modern cosmology. These quantum fluctuations, minute differences in density that arose during inflation, are believed to be the seeds from which galaxies and large-scale structures later grew. Today, this framework of cosmic inflation helps scientists tie the state of the universe just after the Big Bang to the sprawling cosmic structures observed across billions of light years. Several models have been proposed to explain the mechanics of cosmic inflation, each offering a different view of how and why the universe expanded so rapidly. These models diverge primarily in their understanding of the inflaton field, the hypothetical field responsible for driving inflation, and the mechanisms underlying its behavior. One of the earliest and most straightforward models is the new inflation model. This theory suggests that the inflaton field starts in a metastable state, releasing energy and triggering the inflationary expansion. As the field reaches its lowest energy state, inflation ends, transitioning into the reheating phase, where the energy of the universe is converted into particles and radiation. This model proposes a smooth and gradual inflationary period, eventually leading to the birth of the universe we know. Another model, the chaotic inflation model, introduces greater flexibility. In this scenario, inflation can occur under a wide range of initial conditions. The inflaton field may begin in a high-energy state, with different forms of potential energy, ranging from quadratic to exponential, leading to inflation. The chaotic nature of this model suggests that inflation could happen in various ways, regardless of the universe's initial conditions. This model implies that multiple inflationary scenarios could be at play, offering a rich variety of cosmic possibilities. The eternal inflation model takes this idea further, suggesting that inflation may continue indefinitely in certain regions of space. While some regions of the universe stop inflating and form distinct bubble universes, other areas may continue inflating forever. This leads to the idea of a multiverse, where numerous universes exist, each with potentially different physical constants and laws. The concept of eternal inflation paints a vast cosmic landscape, offering theorists a framework to explore a wide array of possible universes emerging from a single inflationary event. The natural inflation model introduces yet another perspective. This model posits that inflation could be driven by axion fields, hypothetical particles linked to theories of the strong nuclear force. Natural inflation aims to connect the study of inflation with the world of elementary particle physics, potentially unifying disparate areas of cosmology and offering new insights into the fundamental forces of the universe. Each of these models presents a unique approach to understanding inflation, addressing different challenges posed by observations of the universe's structure and evolution. As scientists continue to gather data from cosmic observations, such as the cosmic microwave background radiation, the quest remains to refine these models and perhaps discover a single, unified description of the universe's early behavior. The implications of cosmic inflation are profound, reshaping our understanding of the size and age of the universe. Inflation allows for a universe far larger and more complex than previously imagined. Without it, the observable universe might have been limited to regions that could interact with one another, creating significant challenges in explaining the uniformity observed in the cosmic microwave background radiation. However, the rapid exponential expansion during the inflationary period suggests that regions of the universe that are now separated by vast distances were once in close proximity, allowing for the exchange of information and the homogenization of the cosmos. This realization dramatically increases the perceived size of the universe. If the inflationary model is correct, the universe could extend far beyond the regions we can currently observe, stretching into areas that will forever remain beyond our reach. The implications for our understanding of space, time, and the very nature of the cosmos are immense as we continue to explore the mechanisms that shape the universe from the moment of the Big Bang to the sprawling cosmic structures that exist today. The theory of cosmic inflation introduces a groundbreaking approach to understanding the age and evolution of the universe. By examining key features such as the cosmic microwave background, CMB, and large-scale structures, scientists can more accurately estimate the time elapsed since the Big Bang. Inflation, which suggests an incredibly rapid expansion of the universe, offers a framework that smooths out the early conditions, leading to a specific minuscule fraction of time devoted solely to this inflationary period. Once inflation ended, the universe continued to expand, following the laws of cosmic expansion, setting the stage for the present-day structure of the cosmos. This inflationary framework allows for more precise calculations of the universe's age, considering both the inflationary phase and the periods that followed. An essential aspect of this is the interpretation of red shifts in distant galaxies. The redshift phenomenon occurs when light waves stretch as objects move away from us, providing critical data about cosmic expansion. The insights gained from studying inflation help astronomers better interpret these red shifts, especially within the context of an accelerating universe. By refining inflationary models and the subsequent expansion, cosmologists are able to correlate their findings with observed distances, establishing a more comprehensive timeline of the universe's development. By framing the universe within the context of cosmic inflation, scientists gain a clearer understanding of not only its vast size and age, but also the intricate formation and evolution of its structures. This expanded knowledge continues to propel modern cosmology forward, offering answers to some of the most profound questions about our place in the universe. One of the most compelling aspects of inflationary theory involves primordial gravitational waves, ripples in the fabric of space-time that arose during the earliest moments of the universe, possibly during or just after inflation. These waves are a direct result of the rapid expansion of the universe, which creates fluctuations in the gravitational field. Quantum fluctuations could have generated gravitational waves, which, unlike electromagnetic radiation, interact very weakly with matter, allowing them to propagate freely across space. These waves carry vital information about the universe's early conditions, offering a rare glimpse into the cosmos's infancy. The connection between primordial gravitational waves and cosmic inflation is essential for understanding the mechanisms that shape the universe during this transformative era. Many inflationary models propose that the rapid expansion generated tensor modes of gravitational waves, which cause fluctuations in the curvature of space-time. These fluctuations differ from scalar fluctuations, those that correspond to density variations and ultimately gave rise to the galaxies and galaxy clusters we observe today. Detecting primordial gravitational waves would serve as a crucial piece of evidence supporting the theory of inflation. Their discovery would offer direct observational proof of inflation, providing invaluable insights into the energy scales present during the universe's earliest moments. Scientists are actively searching for these waves, primarily by studying their potential effects on the cosmic microwave background. Specifically, they are looking for patterns called B-mode polarization, which are unique distortions caused by gravitational waves passing through the early universe. While definitive evidence for primordial gravitational waves remains elusive, cutting-edge experiments like those conducted by the Laser Interferometer Gravitational Wave Observatory, LIGO, and future space-based missions like LIGO India and the proposed satellite missions are dedicated to detecting these elusive waves. The detection of primordial gravitational waves would not only confirm a central element of inflationary theory, but could also illuminate the fundamental physics of the universe. It would provide a deeper understanding of the forces that were at play during its earliest moments and shed light on the energy landscape of the universe's infancy. The search for these waves represents a tantalizing frontier in cosmology and theoretical physics, offering a chance to unlock some of the universe's greatest mysteries. As future experiments continue to refine our understanding of the early universe, they will be pivotal in either validating or challenging the theory of cosmic inflation. One of the most promising approaches in this ongoing quest is the precise measurement of the cosmic microwave background radiation. Advanced instruments, such as the upcoming space-based Simon Observatory and the CMB-S4 project, are designed to detect the minute fluctuations and polarization patterns in the CMB that could signal the effects of inflation. In particular, scientists will be looking for evidence of B-mode polarization, a telltale signature of primordial gravitational waves generated during inflation. These efforts promise to bring us closer to understanding the intricate and fascinating history of our universe. Large-scale galaxy surveys are pivotal in providing profound insights into the universe's structure and evolution. By mapping the distribution and movement of galaxies across vast distances, astronomers can test predictions made by inflation theory, especially in relation to the statistical properties of cosmic structures that evolved from the tiny fluctuations in the early universe. Surveys like the Vera C. Rubin Observatory will offer a treasure trove of data on galaxy clustering. This data will allow scientists to compare these real-world observations against theoretical models derived from inflationary predictions. Should any discrepancies arise between the observed structures and those forecasted by inflation, this could offer vital clues about the accuracy of these theories. In turn, such findings could challenge or refine our understanding of how the universe began. One of the most promising avenues for verifying inflation theory is the search for primordial gravitational waves. Missions like the Laser Interferometer Space Antenna, LISA, are designed to detect these elusive waves as they travel through the fabric of space-time. Gravitational waves, caused by the stretching and squeezing of space-time itself, hold the key to revealing the energetic conditions that existed during the inflationary epoch. Their detection wouldn't just offer validation of the inflationary model, but would also provide crucial insights into the energy scales at play during the universe's birth, potentially unveiling new realms of physics. In parallel with these observational efforts, advances in particle physics and high-energy experiments could offer indirect evidence in support of inflation. For example, experiments conducted at particle accelerators like the Large Hadron Collider LHC could help uncover candidates for the inflaton field, the hypothetical field believed to drive cosmic inflation. By revealing potential connections between particle physics, the symmetry of fundamental interactions, and field theories consistent with inflationary models, these experiments could either bolster or challenge existing frameworks. Any new particles or interactions discovered might help refine our understanding or alter our views of the mechanisms behind inflation. The road ahead is filled with promise, With breakthroughs in cosmic surveys, gravitational wave detection, and particle physics, researchers are continuously testing the predictions and implications of inflation theory. The quest for definitive evidence remains an exciting frontier in cosmology, one that may profoundly deepen our understanding of the universe's origin and the fundamental mechanisms that shaped its evolution. Time, as understood by physicists, is both a measure of change and a continuum in which events unfold in an irreversible sequence. In classical physics, time is treated as a linear progression, dividing the past, present, and future, allowing events to be ordered and measured in a clear and straightforward manner. However, this simple notion of time becomes far more complex in the realm of modern physics, particularly when considering general relativity. In this framework, time is intertwined with the three spatial dimensions and is influenced by factors such as gravity and the relative motion of observers. Here, time cannot be understood as an independent entity, but rather as a dynamic aspect of the fabric of space-time itself. The concept of time presents a unique challenge when considering the origins of the universe, particularly in the context of the Big Bang. Traditionally, the Big Bang is seen as the event that marks the beginning of both space and time, occurring about 8 billion years ago. This event represents the point at which the universe began to expand from a hot, dense state. In this view, time, as we experience it, began with the Big Bang itself. This suggests that the conventional understanding of time as we know it may not apply to the universe before this pivotal moment. Prior to the Big Bang, there was no time in the sense that we understand it. In fact, the very fabric of time may have only emerged with the birth of the universe. In the field of cosmology, the Big Bang provides the starting point for our understanding of time. From this singular event, scientists have developed models that trace the evolution of the universe, observing how time has progressed hand in hand with the expansion of space. This progression encompasses the cooling of matter, the formation of cosmic structures, and the emergence of galaxies, all unfolding within a temporal continuum that began with the Big Bang. As the universe continued to expand and evolve, physicists have constructed a timeline that tracks the development of the cosmos from its earliest moments to its current state. This evolving timeline serves as a framework through which we explore the universe's past and attempt to understand its future. As the universe expands, its relationship with time raises profound and thought-provoking questions about the very nature of time itself. The ongoing expansion of the cosmos suggests that the rate at which events are perceived to unfold may not be uniform across the vast regions of space. This concept opens up new avenues of inquiry about how time is experienced and measured, especially when considering the grand scale of cosmic evolution. Ultimately, the definition of time within the framework of physics is deeply intertwined with the Big Bang, offering a unique lens through which we can explore the universe's birth and its gradual unfolding. The idea of the arrow of time speaks to the one-way flow of time, a progression where events seem to always move from the past to the future. This concept is intimately linked to the second law of thermodynamics, which states that in an isolated system, entropy or disorder will always increase over time. This natural tendency for systems to evolve toward greater disorder is vividly illustrated in the irreversible processes we witness daily. Take, for instance, a glass that slips from a table and shatters on the floor. Once the glass is broken, there is no way to reverse the process and return it to its original state. This is a direct manifestation of entropy at work. As a result, we experience time as moving in one direction. The past, characterized by lower entropy states, and the future, increasingly marked by higher entropy. The origin of the arrow of time itself can be traced back to the Big Bang. At that pivotal moment, the universe was in a state of intense order with extremely hot and dense conditions. As the universe expanded and cooled, entropy began to rise. The conditions that followed the Big Bang, initially marked by this low entropy state, set the stage for the universe's evolution, establishing the starting point for the continuous flow of time toward greater disorder. Over the course of the universe's evolution, entropy increased steadily, shaped by various processes that took place within the cosmic expanse. These processes, such as the formation of stars, the fusion of elements, and the birth of galaxies, were all pivotal in driving the universe toward a state of greater entropy. Each of these events not only marked a transition, but also represented an increased likelihood of randomness and disorder. As the universe expanded, matter and energy became distributed in more complex ways, and the structures that emerged were statistically more likely to occur than the original ordered conditions. This ongoing expansion and the increasing complexity of cosmic structures further propelled the rise in entropy, reinforcing the one-way flow of time. Interestingly, the arrow of time isn't confined to thermodynamic processes alone. It also manifests in other domains of physics. For example, in biological and psychological contexts, time's direction is often understood in terms of aging, experience, and the passage of life itself. However, it is the thermodynamic arrow of time that serves as the most fundamental basis for our understanding of time's forward movement within the physical universe. Time's unidirectional flow, governed by the relentless increase in entropy, continues to shape the evolution of everything, from stars to galaxies, from planets to life. At its core, entropy is the measure of disorder, of randomness within a system, and it plays a crucial role in both the passage of time and the evolution of the universe. According to the second law of thermodynamics, in any isolated system, entropy will always increase. This means that as time progresses, systems evolve from states of lower entropy, more ordered and organized, towards states of higher entropy, or greater disorder. This progression lies at the heart of what we perceive as time's flow in one direction, from the past to the future, and is often referred to as the arrow of time. In the context of the early universe, the Big Bang marks the moment of extremely low entropy. Initially, the universe was a highly ordered, dense mass of matter and energy. However, as the universe began to expand and cool, the conditions changed and entropy began to rise. The cooling of particles, the formation of atoms, and the subsequent creation of more complex structures like stars and galaxies all contributed to the rise of entropy. Each new step in the universe's development represented a shift toward greater disorder, and as entropy increased, so did the complexity of the cosmos. The transition from the simplicity of the early universe to the complexity of the universe we observe today is a direct result of this fundamental increase in entropy. The relationship between time and entropy can best be understood through the lens of cosmic history. In the early universe, structures were far less complex, and the conditions for life as we know it did not yet exist. Over time, as entropy increased, new structures began to emerge, each more complex than the last. As the universe continued to evolve, the rise in entropy shaped not only the material makeup of the cosmos, but also the very way in which time is experienced. Events unfold in a direction that leads to greater disorder, and this progression has shaped the universe's past, present, and future in ways we are only beginning to understand. Thus, the arrow of time, fundamentally rooted in entropy, shapes the evolution of the universe, driving its expansion and transformation. As time flows inexorably toward greater complexity and disorder, we witness the unfolding of cosmic history, an ongoing journey from a hot, dense, and highly ordered state to one of remarkable diversity and ever-increasing entropy. Galaxies took shape, stars ignited, and over time, a cascade of new physical processes began to unfold, layering the universe with increasing complexity and chaos. This rise in complexity isn't just a random event. It's closely tied to the concept of entropy, which measures the disorder or randomness in a system. As the universe expanded and evolved, its entropy surged, laying the groundwork for the inevitable passage of time. The universe we see today, with its intricate blend of matter and energy scattered across vast stretches of space, represents only a fleeting moment in a much larger cosmic timeline. This intricate arrangement is simply one phase in the ongoing progression, one that will only grow more complex as time marches on. Looking ahead, the future promises even greater levels of entropy. As cosmic processes continue to unfold, stars born, burn, and die, galaxies collide, black holes merge, the entropy of the universe will only increase. This ongoing process frames not only our understanding of the universe's evolution since the Big Bang, but also our projections about its ultimate fate. In essence, the ever-increasing entropy shapes the destiny of cosmic structures, and will ultimately alter the very nature of time as we experience it. One of the most profound ways we attempt to understand this process is through the lens of imaginary time, a concept proposed by physicist Stephen Hawking. Imaginary time stretches our understanding of time itself, moving beyond the familiar past and future. In his work, Hawking made a distinction between real time, the time we live in day to day, and imaginary time, which is a mathematical construct involving complex numbers used in various physical theories. While real time moves in one direction, from past to present to future, imaginary time allows time to take on imaginary values, presenting a completely new perspective on the nature of space, time, and the universe's origin. One of the most groundbreaking aspects of imaginary time is its role in redefining the Big Bang. Traditionally, we picture the Big Bang as the singular point in time where the universe began, a moment of infinite density where the laws of physics break down and space and time collapse into a singularity. But according to Hawking's model, when time is treated as imaginary, the universe's origin no longer carries the baggage of this singularity. Instead, the initial conditions of the universe can be visualized as a smooth, continuous surface, completely removing the boundary of the Big Bang. This means that rather than starting from a sharp point, the universe could be seen as having no edge, no beginning, and no end. Time and space become so intertwined that they no longer exist as separate entities. They are part of a unified, boundless structure. Hawking's imaginary time leads to a completely new way of interpreting the dynamics of the universe. When time is modeled as an imaginary number, the equations that govern the universe's behavior become different, allowing for solutions that don't lead to singularities. This in turn allows for a more unified understanding of the universe's history, one that doesn't break down at the moment of creation. This framework removes the contradictions inherent in the traditional view of the Big Bang and offers a smoother, more continuous path from the origin of the universe to its current state. Hawking's insights also have significant implications for our understanding of cosmology and quantum mechanics. Imaginary time suggests that certain symmetries or hidden features of the universe, which are obscured in real time, may reveal themselves when we approach the cosmos from this new perspective. For example, instead of viewing the universe's expansion as an arrow that moves forward through time, imaginary time allows us to see it as a more static landscape where all possible configurations of the universe coexist. This shifts our understanding of both the events leading up to and following the Big Bang, offering a more integrated, dynamic view of cosmic evolution. Imaginary time doesn't just challenge our existing cosmological models, it fundamentally reshapes them. By allowing time to behave differently, it opens the door to a whole new way of thinking about the universe's beginning and potentially its end. This innovative concept continues to spark research, pushing forward our quest to understand the universe's origin and the fundamental principles that govern its behavior. Alongside these theoretical advancements, Albert Einstein's theory of relativity adds another layer to our understanding of time. One of the key predictions of relativity is the phenomenon of time dilation, which describes how time behaves differently depending on the speed of an object and its position within gravitational fields. This idea is especially important when we consider the early universe, where space and time behaved in extreme ways, especially in the aftermath of the Big Bang. As objects approach the speed of light, time itself appears to slow down for them. This phenomenon becomes increasingly relevant when we look at particles in the early universe. These particles, which traveled at speeds near that of light, experience time at a much slower pace than observers on Earth. To an observer moving at slower speeds, the changes and events in the early universe would appear vastly different. In this light, the formation of cosmic structures and the interactions of particles would take on a new dimension, one that challenges our everyday understanding of time and space. This combination of insights, from the increasing entropy of the universe to the idea of imaginary time, to the relativistic effects that shape how time unfolds, offers a richer, more intricate narrative of the cosmos. Time in all its forms serves as both the canvas and the brush that paints the vast, ever-expanding tapestry of the universe, And as we continue to probe deeper into its mysteries, we find that each layer reveals more profound questions about the past, the present, and the potential future of everything we know. In the vastness of the universe, time does not always unfold as we experience it. Gravitational fields, particularly those found near massive celestial bodies, can warp the fabric of time, creating intense dilations that stretch and compress the moments that pass. In the early moments of the universe, when densities and temperatures were unimaginably high, these gravitational forces were even more powerful, shaping the very evolution of space itself. Understanding how these forces slowed the progression of time, especially near the beginning of the universe, opens a window into the birth of the cosmos. Shortly after the Big Bang, galaxies, stars, and other structures began to form over billions of years, a process influenced heavily by the warped flow of time. These insights not only help scientists piece together the timeline of the universe's formation, but they also allow us to see the deep interconnection between space, matter, and time itself. As we examine the ebb and flow of time, we begin to appreciate its role in the cosmic dance of expansion and evolution, and its central place in shaping the very structure of reality. At the heart of this exploration lies the Wheeler-DeWitt equation, a fundamental concept that emerges from efforts to unite the theories of quantum mechanics and general relativity. This equation offers a window into the nature of the universe at its most fundamental level, describing the universe's wave function in all its possible configurations of matter and energy. Unlike traditional equations in physics, which treat time as an ever-present backdrop against which events occur, the Wheeler-DeWitt equation casts aside time as a variable. In this formulation, the universe exists in a sort of timeless state, where configurations are not framed by the passage of time, but by a vast spatial landscape of possibilities. It presents a mind-bending idea. Time, as we perceive it, may not be an inherent property of the universe at all. The flow of time, the ticking clock of our everyday existence, might be a product of our perception, not an intrinsic aspect of reality. If time is not a fundamental feature of the universe, what does that say about the very nature of existence, causality, and how events unfold? This radical idea calls into question much of what we take for granted about the world we live in. Could it be that time itself is merely an illusion, a construct born of deeper, more complex laws of reality that we are yet to fully understand? The implications are profound, and they extend far beyond abstract theory. This timeless view of the universe has the potential to unravel some of the greatest mysteries in modern physics, such as the paradoxes of black holes and the nature of the Big Bang singularity. Could the universe itself be governed by a deeper set of rules where time is just an artifact of our consciousness? One possible way to interpret these ideas is through the lens of the block universe theory. This theory challenges our conventional understanding of time, proposing that all points in time, the past, present, and future, exist simultaneously in a four-dimensional block. Unlike the flow of time we experience, where moments pass from the past into the present and then into the future, the block universe suggests that time is not a river that flows, but a landscape to be traversed. In this model, the past is fixed, the present is an illusion, and the future is just as real as the moment we are experiencing right now. In the block universe, every moment and event in time coexists, suggesting that our perception of moving through time is simply an illusion created by our consciousness. Our memories, our anticipations, and our experiences of the passing moment are all markers within this greater structure of reality. Time, it seems, may not be the river we thought it was, but rather a vast, unchanging terrain that exists independently of our fleeting experiences. Exploring these ideas forces us to confront deep questions about the nature of reality itself. Is time truly an illusion? And if so, what does that mean for how we understand the universe and our place within it? As we seek to understand the origins and evolution of the cosmos, we may discover that the very fabric of space and time is far more mysterious and far more complex than we ever imagined. Furthermore, this theory is the very foundations of our understanding of free will and determinism. If all events are already mapped out in the block universe, it raises a profound question. Do our choices shape the future, or are they merely the result of a predetermined path? Such a notion invites us to reconsider the very essence of responsibility, existence, and perhaps reality itself. The implications are far-reaching, forcing us to grapple with the intricate relationship between free will, causality, and the fabric of time. This perspective compels us to reflect more deeply on how we experience time and our place within it. It beckons us to reimagine our relationship with the past, present, and future. Are we merely passengers carried by the river of time, or do we hold agency within its flow? These questions are especially poignant as modern science turns its gaze toward reconciling two of its most formidable theories: general relativity and quantum mechanics. The block universe concept offers fertile ground for exploring these existential dilemmas. It encourages us to consider time not just as a linear sequence of events, but as a dimension in the same league as space, an idea that fundamentally reshapes how we perceive the cosmos and our role within it. As the scientific community strives to unite the principles of quantum mechanics with the broader framework of general relativity, the problem of time in quantum gravity emerges as a central issue. In Einstein's general relativity, time is not an abstract concept, but an integral part of the fabric of space-time, dynamically influenced by mass and energy. However, in quantum mechanics, time is treated differently, often viewed as an external parameter, a fixed backdrop against which events unfold. This dichotomy presents a significant challenge in creating a unified theory of quantum gravity. At the heart of this puzzle lies the Wheeler-DeWitt equation, which proposes that the universe exists in a timeless state. In this view, time itself might not be a fundamental aspect of the universe, but rather an emergent property that arises under certain conditions. This revelation could radically shift our understanding of the universe, particularly when we look at the Big Bang. If time breaks down at the singularity, the point where the Big Bang occurred, how do we even begin to describe or comprehend the events that preceded or transpired during that moment? The very nature of time is intricately linked to our understanding of causality and the universe's evolution. If traditional notions of time no longer apply during the extreme conditions of the early universe, how can we interpret phenomena like cosmic inflation, the formation of fundamental particles, and the emergence of structures in the cosmos? Without a clear framework for defining and measuring time, theorists are left with the challenge of developing reliable models for how the universe transitioned from a dense, hot, and chaotic state into the vast, structured cosmos we observe today. This conundrum pushes the boundaries of scientific inquiry, sparking novel approaches to understanding the nature of reality itself. Some theories suggest that time might emerge from more fundamental relationships between physical quantities, potentially offering a new lens through which we can view the universe. Investigating the problem of time in quantum gravity not only illuminates the origins of our universe, but also propels our ongoing research into the very nature of time, reality, and the fundamental forces that govern the cosmos. In the realm of quantum mechanics, different interpretations attempt to tackle the concept of time, often in radically different ways. These diverse perspectives reflect the inherent complexity and richness of quantum theory. Understanding these interpretations is key to unraveling the philosophical and scientific debates surrounding how time operates on the quantum level, particularly when juxtaposed with our everyday macroscopic experiences. One of the most influential interpretations is the Copenhagen interpretation, which asserts that quantum systems exist in superpositions of states until they are measured or observed. In this framework, time is treated as a continuous parameter that governs the evolution of these superpositions according to the Schrödinger equation, providing yet another dimension to our already complex understanding of time and reality. However, this conception introduces significant ambiguities, particularly when considering the nature of time itself, especially in relation to measurement and reality. The act of observation, seemingly the process that collapses the quantum wave function into a definite outcome, suggests that time might be profoundly interconnected with consciousness and the very act of measurement. It raises the question, could time itself be dependent on the observer? Alternatively, the many worlds interpretation, MWI, offers an entirely different perspective. According to MWI, every possible outcome of a quantum event manifests as a separate branching universe, In this framework, time is no longer just a simple linear flow. It becomes part of a much larger multiversal structure. Each quantum event spawns a distinct timeline, with each timeline existing independently in parallel with countless others. Here, time continues to move forward in each individual universe. Yet, the very notion of a singular universal timeline becomes obsolete. Instead, it suggests that every decision or quantum fluctuation results in the creation of a new, divergent path, leading to multiple realities where every possible outcome exists simultaneously. Other theories, like the relational interpretation, propose that time isn't an independent, standalone entity. Rather, it emerges through the relationships between quantum systems. Time, in this view, is not a static backdrop in which events unfold. Instead, it is a product of interactions, an emergent property that arises from the entanglement and interdependence of quantum systems. The passage of time then becomes a byproduct of relational dynamics within the quantum field, an ever-present force shaped by the relationships between particles, waves, and forces. Meanwhile, the de Broglie-Bohm theory, a deterministic model, introduces a more classical sense of time. In this view, particles follow definite trajectories guided by a pilot wave that directs their motion. The theory brings time closer to a deterministic model where events unfold in a predictable manner. However, this interpretation remains controversial due to its implications of non-locality and hidden variables, concepts that challenge the very foundations of quantum mechanics as we understand it today. These varied interpretations underscore the ongoing debates in the realm of quantum mechanics, highlighting the complexities of time and its place within the quantum world. Each perspective brings a unique set of insights, revealing the layered nature of time and inviting deeper exploration and discussion among both physicists and philosophers. As these scholars work to unravel the mysteries of the cosmos, time remains one of the most elusive and enigmatic concepts to comprehend. The idea that time may have had a beginning forces us to reconsider our traditional intuitive understanding of time as an infinite continuum. If time did indeed have a beginning, then there must have been a distinct moment when not just the universe, but the very fabric of time itself came into existence. This concept pushes the boundaries of our comprehension, challenging the assumption that time is a perpetual, unbroken flow. Relating this to the Big Bang theory, we understand that the event took place roughly 13.8 billion years ago, marking the rapid expansion of space and the subsequent formation of matter and energy. This explosion, the origin of both the universe and time, suggests that prior to the Big Bang, there was no before, at least not in the way we understand it. The laws of physics as we know them break down when applied to times prior to the Big Bang, and thus, any attempt to discuss events before that moment is rendered meaningless. Time itself did not exist, and with it, any notion of past or future. This revelation deepens the connection between time and the universe, suggesting that they came into being together. As time began with the Big Bang, so did the universe. Together, they emerged as inseparable phenomena, coalescing into existence at that very instant. But if time did indeed have a beginning, it invites profound philosophical reflection. What, if anything, existed before the Big Bang? Was there a state of pre-time that cannot be conceived of using the language of physics? Several theories attempt to provide answers, such as cyclic models of the universe, which suggest that the cosmos undergoes an eternal cycle of expansion and contraction. Another possibility is the multiverse theory, which posits that our universe is merely one among many, each with its own timeline and set of physical laws. In either case, the question remains, could time as we know it have existed in these pre-Big Bang conditions? Or, as some theories suggest, was time itself an invention born from the Big Bang, emerging only when the universe began its expansion? Ultimately, these perspectives engage with one of the most profound questions about the cosmos. Is time a fundamental pre-existing feature of reality, or is it a relative, emergent phenomenon shaped by the very fabric of the universe itself? As our understanding of quantum mechanics, the Big Bang, and the nature of time continues to evolve, so too will our understanding of the most elusive and vital dimension of existence, time itself. The notion of a temporal beginning has profound implications for our understanding of causality and the very nature of reality itself. It disrupts traditional views of cause and effect, as the absence of time challenges the conventional ideas of before and after. Without time, the sequence of events and the relationship between past, present, and future become meaningless. This presents the beginning of time as not just a point of origin, but a profound boundary, one that invites us to continually explore and question the origins of existence, the interplay between time and space, and the eventual fate of a universe that continues to expand. Space-time, the unified model that merges the three spatial dimensions with the one dimension of time, creates a four-dimensional continuum. This concept, grounded in Einstein's theory of relativity, fundamentally transformed our view of the universe. Whereas space and time were once seen as separate entities, space-time treats them as interconnected and interdependent. Events occur in specific locations at specific moments, offering a more integrated perspective of the cosmos. When applied to the context of the Big Bang, this unified concept becomes even more crucial. Before the Big Bang, space-time itself may not have existed in the form we recognize today, or it may have been radically altered. The Big Bang was not only the birth of matter and energy, but also the inception of space-time as we understand it. The universe's rapid expansion in the moments that followed marked the stretching of space-time, and with this stretching came the formation of galaxies, stars, and eventually the larger structures of the cosmos we see today. The fabric of space-time is not static. It is influenced by the presence of mass and energy, curving and bending in response. This curvature is what we experience as gravity, determining how objects move and interact across the universe. In the aftermath of the Big Bang, space-time was deeply distorted, shaped by the extreme densities and temperatures of the early universe. Understanding how these conditions influence the initial expansion is key to understanding the universe's unfolding history, its current structure, and what its future might hold. This view of space-time highlights the interconnectedness of time and distance, revealing that both are woven into the very fabric of the universe. As researchers continue their quest to unravel the mysteries of cosmic evolution and reality itself, the interplay between space and time remains a foundational concept. It is through this lens that phenomena such as black holes, gravitational waves, and the cosmic microwave background radiation echoes of the Big Bang are explored. Einstein's theory of general relativity dramatically reshapes our understanding of space, introducing the idea that space is not a mere backdrop, but a dynamic entity intertwined with time. According to general relativity, mass and energy affect the structure of space, causing it to curve or warp. Rather than thinking of gravity as a force acting at a distance, this theory reveals gravity as a manifestation of space-time geometry. Massive objects like planets and stars warp the space-time around them, creating gravitational wells. These curvatures dictate the paths objects take as they move through the cosmos. For example, planets do not orbit a star in a straight line. Rather, they follow curved paths, shaped by the star's mass bending the space-time fabric. This new perspective of gravity fundamentally alters our understanding of how celestial bodies interact, shifting the narrative from a force-based view to one rooted in geometry. Moreover, general relativity reveals that time itself is influenced by gravity. Time moves more slowly in stronger gravitational fields, a phenomenon known as gravitational time dilation. This means that if you were to stand near a massive object like a black hole, time would pass differently for you compared to someone far from it. This observation further emphasizes the deep interconnection between space and time. The consequences of general relativity are immense. They not only transform our understanding of gravity, but also open new windows into phenomena such as black holes, gravitational waves, and the expansive nature of the universe. The theory challenges long-standing assumptions about space, revealing it to be a dynamic, living fabric shaped by the distribution of mass and energy throughout the cosmos. It sets the stage for deeper explorations into the origins of the universe, including the conditions that existed shortly after the Big Bang. The theory provides a framework for understanding the intricate motion of celestial bodies and the unfolding dance of the cosmos. The idea of curved space-time emerges directly from Einstein's general theory of relativity, which illustrates that mass and energy bend the fabric of space and time. In this framework, space-time is not a flat, passive backdrop, but a dynamic, ever-changing entity. Imagine placing a heavy object on a trampoline. The surface sags and curves around the object, creating a depression. This analogy helps to visualize how the distribution of mass in the universe causes space-time to bend and warp. Objects that move through this curved space-time follow paths dictated by its geometry, without the need for a force acting across distances. In the context of the early universe, the curvature of space-time was vital in shaping the conditions that existed immediately after the Big Bang. In those first moments, the universe was condensed into an infinitely dense, hot state, with space-time itself being heavily warped. This extreme curvature influenced every physical interaction and laid the groundwork for the phenomena that followed. As the universe began to expand, space-time itself stretched, shaped by the distribution of energy and matter emerging during this phase. The rapid expansion and the accompanying changes in space-time curvature played a significant role in the universe's evolution, influencing the formation of matter and energy, and leading to the creation of galaxies, stars, and other large-scale structures. As the universe continues to expand, it does so through the stretching of space-time. Distances between objects increase as the universe grows, reflecting dynamic shifts in curvature over time. This ongoing expansion not only reveals the intricate relationship between time and space, but also provides a deeper understanding of the universe's past, present, and future. Space-time, in its most fundamental form, is anything but static. The intricate fabric of the cosmos is shaped by both grand cosmic forces and minute quantum fluctuations, each leaving their indelible mark. The curvature of space-time is not just an abstract concept, but a crucial player in explaining the most profound events in the history of the universe. Take, for example, the phenomenon of cosmic inflation, which unfolded just moments after the Big Bang. In the briefest of moments, the universe expanded at an astonishing rate, with space-time itself undergoing transformations so extreme that they reshaped the very structure of the cosmos. This rapid expansion sowed the seeds of a universe that would, over billions of years, evolve into the vast, relatively homogeneous and isotropic cosmos we observe today. The transformation of space-time during inflation wasn't just a fleeting event. It set the stage for the broader structure of the universe. By understanding how space-time itself is not a mere backdrop, but an active participant in the unfolding of the cosmos, we gain a deeper insight into the origins and evolution of the universe. It turns out that space-time isn't a passive stage where events unfold. It is an active force, dynamically shaping the history of everything we know. At the extreme end of space-time, where the most enigmatic phenomena occur, we encounter singularities. These are the regions where the known laws of physics break down. Singularities, which are marked by infinite density and the curvature of space-time, defy conventional understanding. Black holes, for instance, are perhaps the most well-known examples of singularities. In a black hole, the collapse of a massive star results in a region so compressed that space-time itself curves infinitely. But it isn't just black holes that contain singularities. The Big Bang itself originated from a singularity, an infinitesimally small point where all matter and energy were packed together, infinitely dense and hot. From this singularity, approximately 13.8 billion years ago, the universe began its expansion, giving rise to the space and time we experience today. The singularity at the dawn of the universe represents a boundary, one where our understanding of space and time crumbles. Discussing what happened before the Big Bang becomes an almost impossible task, as time itself was born from this initial singularity. Within the chaotic conditions of the Big Bang singularity, both general relativity and quantum mechanics, the two pillars of modern physics, fail to integrate in a meaningful way. This creates an intellectual chasm, one where answers remain elusive. It is here that the mysteries deepen, as these singularities challenge not only the laws of physics, but also the philosophical foundations of causality. What does it mean for events to happen when time itself has yet to emerge? This paradox leads to fundamental questions about the very nature of the universe. The connection between singularities and the Big Bang raises a host of fascinating inquiries that go beyond the boundaries of physics. The very existence of a singularity at the birth of the universe suggests that the conventional understanding of space and time is woefully incomplete. It calls for the development of new, more integrated theories, such as string theory or loop quantum gravity, that might offer a coherent explanation for what transpired at or before the Big Bang. Singularities, in their mysterious and often incomprehensible nature, highlight the limitations of our current theories and underscore the need for a unified framework that can bridge the gaps between relativity and quantum mechanics. But singularities, while enigmatic and full of riddles, are also gateways. They invite us to peer deeper into the fundamental nature of reality itself, pushing the boundaries of scientific research and inspiring new avenues of exploration into the origins and evolution of the universe. They serve as a reminder that the cosmos, with all its complexities, still holds secrets waiting to be uncovered. As we venture further into the microscopic realm, quantum foam emerges as another tantalizing concept. Rooted in the bizarre principles of quantum mechanics, quantum foam attempts to describe the very fabric of space-time at its smallest scales, particularly the Planck length, which is approximately 10 to the power of negative 35 meters. At these minuscule scales, space-time is anything but smooth and predictable. Instead, it behaves in a turbulent and chaotic manner, constantly fluctuating due to the energy disturbances in the quantum field. The term quantum foam was first introduced by physicist John Wheeler, who envisioned space-time as a frothy, turbulent sea of energy. At the Planck scale, the fluctuations in energy are so intense that they give rise to fleeting, ephemeral structures that resemble bubbles or foam. These fluctuations might cause space-time to warp and contort, creating virtual particles and geometrical distortions that appear and vanish within the blink of an eye. The idea is revolutionary. Space-time is not a fixed arena in which events take place, but a dynamic, ever-changing entity that is constantly influenced by the quantum fluctuations occurring beneath the surface. This concept challenges our traditional understanding of space and distance. At these infinitesimal scales, distances themselves may lose their usual meaning. The smooth geometry of space-time, which we take for granted at macroscopic scales, becomes profoundly disrupted. The implications of this are far-reaching. It hints at a deeper, more complex structure to reality, one that is shaped by quantum principles in ways we have yet to fully understand. Quantum foam provides an intriguing glimpse into the nature of space-time at the smallest levels, offering a potential framework for uniting the two great theories of modern physics, general relativity and quantum mechanics. By reconciling these theories, we might finally unlock the secrets of the universe, bridging the gap between the vastness of space and the minuscule world of quantum particles. As we strive to comprehend the fundamental building blocks of reality, concepts like quantum foam remind us that the universe is far more intricate and interconnected than we could ever have imagined. If quantum foam shapes the smallest scales of space-time, it could dramatically reshape our entire understanding of gravity, black holes, and even the origins of the universe itself. By delving into quantum foam, physicists are granted the opportunity to peer into the very fabric of existence, questioning how this chaotic structure at the microscopic level might impact the larger universe we observe. In essence, it serves as a humbling reminder that the universe could be far more intricate and complicated than our everyday experiences would lead us to believe. The holographic principle offers a mind-bending perspective on the nature of space, proposing that the three-dimensional reality we experience could in fact be an illusion, one encoded on a two-dimensional surface. This idea arises from the convergence of quantum mechanics, general relativity, and information theory. It suggests that all the information within a volume of space might be represented on its boundary, much like a hologram encodes a three-dimensional image onto a two-dimensional surface. At the heart of this principle lies a revelation drawn from black hole physics. According to the laws of black hole thermodynamics, the area of a black hole is linked to the amount of information it can hold. This leads to a groundbreaking realization. The entropy, or informational content, of a region of space doesn't depend on the volume within that space, but rather on the information encoded at its boundary. This challenges our understanding of space itself, hinting that the familiar three-dimensional world around us might be a projection of two-dimensional data stored on some distant surface. This concept opens up profound questions about the true nature of reality. If space is merely a projection of information from a boundary far away, it suggests that what we perceive as the solid, tangible universe may not be as substantial as it seems. Instead, it might be a manifestation of deeper, more fundamental information. This view implies that the physical universe is inextricably connected to the interaction of information and the laws governing that information. As such, the holographic principle has drawn significant attention in the search for theories of quantum gravity and the nature of space-time, prompting scientists to reconsider how dimensions and reality might function at their core. This paradigm shift encourages the exploration of entirely new frameworks to describe the cosmos. In doing so, researchers hope to unlock mysteries about the behavior of black holes and the very origins of the universe. While it challenges our intuitions about space and existence, it also offers the potential for groundbreaking insights into the very structure of the cosmos. Non-commutative geometry, a more advanced mathematical framework, extends traditional geometry by allowing space coordinates to behave like quantum mechanical operators, where the order of operations matters. In classical geometry, coordinates are commutative, meaning the position of points can be measured without worrying about the sequence of operations. However, non-commutative geometry suggests that at extremely small scales, especially near conditions like those right after the Big Bang, the spatial coordinates might not commute, leading to a complex and intricate geometry that defies classical understanding. This new approach has profound implications for our grasp of space-time, particularly within the context of quantum gravity. The universe's earliest moments following the Big Bang were characterized by extreme energy densities and temperatures. Under such conditions, the conventional view of smooth, continuous space-time breaks down, suggesting that the fabric of space itself could be governed by the principles of non-commutative geometry. In such an environment, distances and the relationships between points could become uncertain or layered in ways that traditional physics cannot account for. Incorporating non-commutative geometry into modern physics allows for models that bridge the gap between general relativity and quantum mechanics. These models offer a vision of space-time as a dynamic, ever-changing entity, one influenced by quantum fluctuations. This concept supports the idea of a foamy or fluctuating space-time, similar to quantum foam, in which conventional notions of smooth and continuous space simply do not apply. By embracing non-commutative geometry, researchers can investigate the intricate behavior of singularities, like those found at the center of black holes or at the very moment of the Big Bang. It provides a framework for understanding the universe at its inception and the laws that govern its birth. Finally, loop quantum gravity offers another compelling approach to unify general relativity and quantum mechanics. Rather than viewing space as a smooth continuum, this theory proposes that space is composed of discrete, quantized units, often referred to as loops. These loops represent the smallest possible lengths, the fundamental building blocks of the fabric of space itself. Within this framework, the geometry of space is not a continuous structure, but rather a complex network of interconnected loops. These loops form a granular structure, similar to a finely woven fabric, where each individual loop plays a role in shaping the connections between different regions of space. In this way, loop quantum gravity redefines the way we conceive of space, transforming it from a smooth, continuous entity to a granular quantum structure. This shift fundamentally alters how we think about distances and geometric relationships, especially at incredibly small scales. By embracing the idea of discrete space, loop quantum gravity promises to provide new insights into the fundamental nature of space-time and the universe itself. Loop quantum gravity offers a revolutionary perspective on some of the most puzzling phenomena in physics. One of its most profound insights is its ability to address the concept of singularities. In traditional models of general relativity, singularities, like those found at the centers of black holes or during the Big Bang, are regions where density and curvature are thought to become infinite, causing a breakdown in the laws of physics. However, loop quantum gravity challenges this view. It suggests that under such extreme conditions, space-time doesn't collapse into a singularity. Instead, it behaves in a way that avoids the formation of infinite values. The quantization of space offers a stable structure, friend Kang, helping to preserve the laws of physics even at these extreme points. This concept opens the door to a more robust understanding of both time and space, even as the universe reaches back to the moment of its birth. Moreover, loop quantum gravity goes a step further by incorporating the dynamic nature of space-time itself. In this framework, space-time is not a static backdrop, but a fluid and evolving entity influenced by the quantum properties of its fundamental components. The interactions between quantum loops govern the very geometry of space, leading to an ever-changing structure that evolves over time. This evolving nature of space-time provides deeper insights into cosmic phenomena, including the origins of the universe, making loop quantum gravity a leading candidate in the quest to unify quantum mechanics with general relativity. Through this approach, scientists are working to reveal the intricate connections between space, time, and the fundamental forces of nature. Parallel to loop quantum gravity, there is another promising approach within quantum gravity research known as causal dynamical triangulation. This method attempts to describe space-time as a collection of basic building blocks like triangles or higher dimensional simplices. By combining principles from both quantum field theory and general relativity, causal dynamical triangulation offers a unique way to investigate how the complex structure of space-time emerges from fundamental quantum processes. In this framework, space-time is constructed from discrete geometric pieces arranged in ways that preserve causality, the fundamental rule that governs the cause and effect relationship between events. Researchers sum over all possible configurations of these simplices, exploring different ways space-time could manifest at the quantum level. The triangulation is governed by specific rules that dictate how these pieces connect and evolve. From this, a coherent space-time structure gradually emerges, viewed from a fundamentally quantum perspective. The beauty of this model lies in its ability to show how the smooth, continuous space-time we observe at macroscopic scales could emerge from the quantum realm. As researchers examine larger scales of the triangulated structure, they find that the effective geometry of space-time begins to resemble the curved, smooth fabric of our universe. This suggests that the space-time we experience is, in essence, an emergent property of more fundamental quantum processes. Furthermore, causal dynamical triangulation provides valuable insights into the behavior of space-time at the smallest scales. By analyzing the statistical properties of triangulated spacetimes, researchers can explore how key concepts like distance, volume, and curvature arise. These findings offer crucial connections with cosmological theories and the origins of the universe. This avenue of research is a promising path forward in reconciling space-time dynamics with quantum mechanics, shedding light on some of the most fundamental questions about the nature of reality itself. String theory, another cornerstone of modern physics, introduces yet another mind-bending concept: extra dimensions. Beyond the familiar 3 spatial dimensions and 1 time dimension, string theory proposes that there are additional dimensions, curled up and compactified in such a way that they are not directly observable at macroscopic scales. These hidden dimensions have profound implications, particularly during the early moments of the universe, right after the Big Bang. In the context of the early universe, these extra dimensions can influence the behavior of fundamental interactions and the formation of particles. String theory posits that the building blocks of matter are not point-like particles, as traditionally thought, but rather one-dimensional entities called strings. The way these strings vibrate, according to the shape and structure of the extra dimensions, affects the properties of the particles they produce. This leads to the emergence of different types of particles and forces, shaping the fundamental structure of the universe we observe today. The vibrational modes of strings in these extra dimensions could help explain the variety of fundamental forces in nature, including gravity, electromagnetism, and the strong and weak nuclear forces. By unraveling the ways in which strings vibrate, string theory promises to offer a deeper understanding of the universe's intricate design, potentially unifying all the forces of nature into a single theoretical framework. In all of these approaches, loop quantum gravity, causal dynamical triangulation, and string theory, science is edging closer to a deeper understanding of the fabric of space-time and the fundamental forces that govern the universe. These theories are not just abstract ideas, they hold the potential to unlock answers to some of the most profound mysteries of existence. As we explore these frameworks, we move closer to comprehending the true nature of reality itself, revealing the intricate, interconnected web of forces, dimensions, and quantum processes that make up our universe. Moreover, extra dimensions may offer a fascinating mechanism for cosmic inflation, a theory suggesting that the universe underwent a rapid and exponential expansion right after the Big Bang. During this brief but critical inflationary period, the very fabric of space-time could have been shaped and influenced by the geometry of these extra dimensions. In turn, this would have affected how energy was distributed throughout the early universe, catalyzing the swift and nearly uniform growth of space. The result? A cosmos that, at large scales, appeared isotropic, essentially the same in every direction. This rapid expansion could have set the stage for the conditions we now observe in the large-scale structure of the universe, such as galaxies, clusters, and vast cosmic voids. The connection between the familiar four dimensions of space and time and these hidden extra dimensions doesn't just provide a potential explanation for the universe's expansive growth. It also opens the door to groundbreaking insights into other fundamental cosmological phenomena. Take black holes, for example. The nature of these dense cosmic objects might be profoundly altered by the existence of extra dimensions. Additionally, certain models propose that gravity, which we typically experience as a force acting only within our four-dimensional universe, might propagate into these extra dimensions. This idea could revolutionize our understanding of gravity's behavior, especially in the chaotic and extreme conditions of the early universe. It may also offer new paths for integrating gravity with the other fundamental forces in a unified theory, potentially solving one of the most elusive challenges in modern physics. The incorporation of extra dimensions into string theory broadens our understanding of the early universe, offering promising explanations for its origins, the fundamental nature of particles, and the dynamics that shaped its rapid expansion. As researchers continue to delve into these complex relationships, the role of extra dimensions remains a pivotal focus in the ongoing quest to unravel the profound mysteries of our universe's origins. The question of whether something can truly come from nothing has long been a profound enigma, drawing the attention of physicists, philosophers, and cosmologists alike. In the realm of scientific inquiry, this puzzle often focuses on the origins of the universe, particularly what transpired during the Big Bang and what empty space might really entail. In classical terms, nothing is simply the absence of matter, energy, and even the fundamental laws of physics. But in the strange, counterintuitive world of quantum mechanics, the concept of nothingness becomes far more complicated. Quantum field theory challenges our traditional understanding by suggesting that what we perceive as empty space is anything but. Rather, it is teeming with fluctuating energy, and virtual particles constantly flicker in and out of existence. These fleeting phenomena might seem like the stuff of theoretical physics, but they provide crucial insights into the true nature of the vacuum. This means that even in a perfect vacuum, commonly regarded as the epitome of nothing, there are still constant fluctuations of energy that can create transient particles and forces. Some interpretations of these quantum fluctuations even propose that such temporary disturbances could have catalyzed the creation of the entire universe. According to one compelling idea in modern cosmology, the universe may have originated from a quantum fluctuation within a vacuum state. Under certain extreme conditions, a region of space could have experienced a fluctuation so intense that it generated matter and energy, leading to an event similar to the Big Bang. This theory fits neatly with the concept that the universe could emerge spontaneously from a state of quantum nothingness, where the laws of physics themselves permit the creation of matter and energy without a pre-existing cause. In this view, the very notion of nothing is transformed from an empty void into a fertile ground for creation, where the universe could arise from the quantum fluctuations of a seemingly empty space. It challenges our deepest intuitions about the origins of existence and may provide the key to unlocking the most profound mysteries of the cosmos. In the ongoing exploration of the universe's origins, the question of time itself presents a deeply challenging paradox. If time emerged with the Big Bang, the very idea of before loses all meaning, complicating not only our understanding of the universe's creation, but also the essence of causality. How can we define creation when the concept of time itself is bound to the birth of the universe? Some theories offer intriguing perspectives, suggesting that our universe might be part of a broader cosmic cycle, a pattern of perpetual expansion and contraction. Such models propose that time is not a linear progression, but a recurring cycle that might repeat itself across cosmic epochs. This suggests that the universe could exist in various states, perpetually creating and recreating itself. In this framework, the Big Bang could represent just one of many births of the cosmos, part of an infinite loop where the boundaries of time stretch beyond any individual event. Yet, this idea raises a profound challenge to our intuition. The notion that something, anything, can arise from nothing runs counter to our everyday understanding of existence. And yet, physicists, by venturing into the realms of quantum theory and cosmology, are increasingly probing these very questions. As their research delves deeper into the origin of the universe, it illuminates the mysteries surrounding the Big Bang, offering new possibilities that might bridge the gap between physics, philosophy, and our broader understanding of reality. The question of what existed before the Big Bang carries with it a deep philosophical paradox. Traditionally, the Big Bang has been seen as the moment when not only the universe but also time itself came into being. In this view, time emerged from a singular cosmic event, and before that, time, as we understand it, simply did not exist. This challenges our conventional understanding of causality and chronology. Time is no longer a backdrop for events to unfold. It is intricately woven into the fabric of space itself. Without time, there is no temporal flow, no sequence of events that could lead to anything we might recognize as before. The absence of before suggests that human language and understanding are inadequate when it comes to grasping the true nature of the cosmos. How can we describe the conditions that existed prior to the Big Bang if the very concepts of before and existence are inapplicable? This tension is at the heart of various cosmological models that attempt to explore these mysteries. One such model is the cyclic universe, which posits that the universe undergoes infinite cycles of expansion and contraction. In this view, the Big Bang is not a singular, unique event, but part of an endless series of cosmic births and deaths. Time, in this scenario, stretches infinitely backward and forward, making the question of before less relevant in a universe defined by continual rebirth. Other theories propose even more radical ideas, such as the multiverse hypothesis, which posits that our universe is but one of countless others, each with its own set of physical laws and timelines. In this view, the concept of time might be entirely different across various universes, suggesting that even if time did begin with the Big Bang in our universe, other parallel frameworks might operate outside the temporal constraints we are familiar with. These models offer glimpses into the possibility that time, as we know it, may not be the ultimate truth of existence. Such explorations ultimately reveal the limits of human understanding when it comes to the fundamental questions of creation and existence. The more scientists and philosophers probe these mysteries, the clearer it becomes that our perceptions of reality are bounded by the constraints of human cognition. The pursuit of answers to these questions pushes the boundaries of our intellectual horizons and underscores the importance of continued inquiry into the nature of time, space, and the cosmos. At the same time, the question of the universe's origin has profound philosophical and cultural implications. Many religions and cultures have developed creation myths that attempt to explain the universe's origins, reflecting their unique worldviews and values. These creation stories often address fundamental questions about the nature of existence, the origins of life, and humanity's place in the cosmos. As scientific theories, particularly the Big Bang theory, have gained widespread acceptance, many religious traditions have sought to reconcile these new insights with their sacred teachings. For some religious thinkers, scientific discoveries provide an opportunity to reinterpret sacred texts in a way that aligns with modern cosmology. These thinkers often suggest that the evolving nature of the universe and the scientific explanation of the Big Bang can be seen as expressions of the divine. In these interpretations, science and faith are not at odds but complement one another. Science offers explanations of the universe's mechanics, while religion provides deeper insights into its meaning and purpose. In contrast, other religious traditions may see the scientific explanation of the universe's origins as fundamentally at odds with their creation narratives. For those who hold literal interpretations of sacred texts, the notion of the Big Bang as a purely natural event may pose a direct challenge. In such contexts, there are those who propose that divine intervention played a role in the universe's formation, positioning the Big Bang as a moment of creation orchestrated by a higher power rather than an entirely natural phenomenon. As the boundaries between science and religion continue to evolve, the question of what came before the Big Bang remains at the heart of the larger conversation about the nature of reality, existence, and the origins of the cosmos. It is a question that invites both scientific inquiry and philosophical contemplation, pushing humanity to confront the unknown and seek understanding at the limits of what we can comprehend. Indigenous cultures around the world have long carried creation stories that are deeply intertwined with their understanding of the land and the natural world. These narratives are not just tales, they are a reflection of the cultures from which they emerge, woven into the fabric of their ecological and spiritual life. At the heart of these stories is an enduring message: balance, interconnectedness, and the inseparable relationship between humans and the earth. In these traditions, the world is not something to be conquered, but a living, breathing entity to be revered and understood. They speak of a universe where humans exist in harmony with nature, with each living being, plant, and rock holding a specific role within the greater cosmic dance. What is striking, however, is how these indigenous creation stories don't necessarily stand in opposition to scientific theories, but can coexist with them. These narratives offer rich layers of meaning and insight that enhance our modern understanding of the universe, intertwining ancestral wisdom with the latest cosmological discoveries. As our awareness of science and cosmology expands globally, there has been an increasing dialogue between scientific and religious communities, an exchange that has opened doors to deeper, more nuanced understandings. In this shared space, both science and spirituality have room to inform one another, creating a richer, more diverse exploration of humanity's place within the cosmos. The reconciliation of these creation myths with scientific theories remains, however, a dynamic and ongoing process. It is constantly shaped by cultural contexts, philosophical inquiries, and the eternal quest for meaning in a universe that often feels too vast to comprehend. This is particularly evident when we confront one of the most profound questions that has preoccupied humanity for centuries. Is the universe finite, or is it infinite? This simple question reverberates through scientific, philosophical, and spiritual discussions, as it influences not only our understanding of the cosmos, but also our sense of self, purpose, and existence. A finite universe suggests that the cosmos has limits, a boundary beyond which there is nothing. If the universe is finite, it may have had a specific origin, perhaps the Big Bang, which serves as the universe's starting point, marking the birth of time itself. This idea evokes deep philosophical questions. What existed before the universe? Was there ever a before? Or has time always been bound to the universe's own existence? And when the universe eventually reaches the end of its evolution, what will that end look like? Will it collapse in on itself or simply fade into nothingness? In contrast, an infinite universe raises questions of a different magnitude. If the universe extends endlessly in all directions, it becomes an unbounded expanse, stretching beyond our capacity to comprehend. An infinite cosmos opens up intriguing possibilities. Could it mean that there are infinite variations of life, infinite worlds, infinite occurrences of similar events unfolding simultaneously across an endless stretch of time and space? This idea challenges our sense of uniqueness and raises deep questions about the significance of our existence. If there are infinite worlds, is it possible that similar versions of ourselves exist elsewhere? experiencing the same lives, making the same choices, and asking the same questions. The idea of an infinite universe also carries profound implications for our understanding of space-time and the laws of physics. If the universe is infinite, it suggests that certain physical constants, like gravity or the speed of light, may be consistent throughout. In this scenario, the universe would appear to be homogeneous on a grand scale. Yet, within this vastness, we might be in a localized patch that is finite and observable, suggesting that while we perceive the universe as structured and limited, the true cosmos may be infinitely larger and more complex than we can ever truly grasp. This distinction between finite and infinite universes also invites deep philosophical reflection on time itself. In a finite universe, time would have a clear beginning and a potential end. The beginning could be marked by an event like the Big Bang, while the end could be the universe's eventual demise. This raises profound questions. What is the ultimate fate of existence? In an infinite universe, however, time might be understood as an eternal continuum with no definitive starting or ending points. The very concept of eternity becomes real, raising questions about cyclical patterns of existence, whether the universe and life itself are in an endless loop of birth, death, and rebirth. Ultimately, whether the universe is finite or infinite has far-reaching implications, not just for the science, but for existential questions about our purpose, our place, and the nature of consciousness. These questions are not just academic, they shape how we view ourselves in relation to the cosmos. The ongoing exploration of these concepts continues to evolve as new discoveries emerge and old beliefs are reconsidered. As we delve deeper into the mysteries of the universe, our understanding of reality and our place within it continues to unfold, layer by layer, insight by insight. One key philosophical consideration that arises in this discussion is the anthropic principle, which suggests that the fundamental properties of the universe are conditioned by the necessity for conscious beings like humans to exist. There are two main forms of this principle, the weak anthropic principle and the strong anthropic principle. The weak version proposes that the universe's observable properties must be compatible with life, while the strong version argues that the universe must possess the conditions necessary for life to develop at all. The anthropic principle holds particular weight in discussions about the origin of the universe. When considering the vast range of physical constants, such as the force of gravity or the mass of elementary particles, the anthropic principle suggests that if any of these constants were even slightly different, intelligent life would not have emerged. This observation leads to the intriguing reflection that the universe appears to be fine-tuned for life. But why? Why does the universe have these particular characteristics? In the context of cosmological theories like the multiverse hypothesis, the anthropic principle gains even more significance. Some theorists suggest that our universe is just one of many, each governed by its own set of physical laws. In this view, it is not surprising that our universe has the conditions conducive to life, because in the vastness of the multiverse, we can only observe the one that happens to support our existence. The anthropic principle in this light offers a lens through which to understand why the laws of nature in our universe seem uniquely suited to life. We are, after all, inhabitants of a cosmos that just happened to develop in ways conducive to our being. Furthermore, the anthropic principle sparks profound philosophical debates surrounding the nature of purpose and existence itself. It compels us to consider whether the fundamental properties of the universe are mere products of chance, or if they hint at a deeper, more intentional design. This intersection between scientific theories of the universe's origins and the anthropic principle opens a wide avenue for exploring not only the cosmos, but also the very essence of life itself. Scientists and philosophers alike find themselves drawn into a multi-dimensional dialogue, pondering the vastness of the cosmos and our own place within it. In a universe so finely tuned that it raises the question, is our existence a fortunate accident, or does it reflect something more? The pursuit of understanding the universe's origins carries with it significant ethical concerns that stretch far beyond scientific inquiry alone. One of the most pressing ethical considerations involves the role of scientists and researchers in communicating their findings. As our understanding of the cosmos deepens, from the complexities of the Big Bang to the mysterious behavior of black holes and quantum mechanics, the need to make these intricate concepts accessible to the public becomes essential. Without careful translation into layman's terms, the public is at risk of misunderstanding or misinterpreting these profound discoveries. Misinformation can breed skepticism and distrust, possibly undermining the very institutions that strive to advance our collective knowledge. Moreover, delving into the universe's origins inevitably brings us face to face with existential questions about our significance in the grand scale of the cosmos. Discoveries that underscore the fragility of humanity within the vastness of space can evoke feelings of insignificance, or worse, existential dread. These emotional and philosophical reactions prompt difficult ethical questions about how society should engage with such realizations. What does it mean to be human in a seemingly indifferent universe, and how does that understanding shape our values, our priorities, and our relationships with one another? Navigating the emotional and philosophical impacts of these discoveries requires more than just scientific clarity. It demands a compassionate and inclusive dialogue that encompasses a variety of perspectives, ensuring that the societal impact of such revelations is fully considered. Another facet of the ethical discussion centers on the allocation of resources for cosmological research. Grand projects, such as the construction of large particle colliders and space telescopes, require vast financial investments. Society must weigh the potential benefits of advancing our understanding of the cosmos against pressing issues that demand immediate attention, such as poverty, climate change, and healthcare. The debate over prioritizing scientific exploration in cosmology versus addressing these urgent human needs is fraught with tension, raising ethical questions about our collective responsibilities. How do we balance the thirst for knowledge with the moral obligation to address humanity's most pressing challenges? As we push further into the unknown, the pursuit of cosmic knowledge also leads to moral considerations about the potential consequences of our discoveries. The more we uncover about the fundamental nature of the universe, and the more we manipulate concepts at the quantum level, the greater the moral responsibility becomes. The technologies that emerge from this understanding, particularly in fields like quantum computing, artificial intelligence, and space exploration, offer immense potential, but also carry significant risks. There is an urgent need for a proactive approach to ensure that these advancements serve the greater good of humanity, rather than perpetuating existing inequalities or giving rise to new ethical dilemmas. How do we ensure that these powerful tools are harnessed for the benefit of all, and not just a privileged few? In sum, the quest to understand the universe's origins is not just a scientific endeavor, it is a profound ethical journey. From the responsibility of clear scientific communication to the existential implications of our discoveries, from debates about resource allocation to the moral consequences of emerging technologies, these ethical dimensions must be considered if we are to pursue cosmic exploration in a responsible and inclusive way. Our expanding understanding of the universe is beginning to shape the very way we conceive of its potential end, influencing both our scientific theories and our philosophical reflections. The Big Bang Theory, which proposes that the universe began in an incredibly hot and dense state around 13.8 billion years ago, set the stage for the concept of cosmic evolution. This expansion led to the formation of galaxies, stars, and planets, providing a backdrop for imagining possible futures for the universe. According to various cosmological models, the universe's eventual fate may follow several dramatic paths. The Big Freeze, in which the universe continues to expand indefinitely, becoming a cold, dark, and lifeless expanse. The Big Crunch, where gravitational forces reverse the expansion, collapsing the universe back into a singular state. Or the Big Rip, in which the accelerating expansion of the universe tears everything apart. Each of these scenarios reflects a continuation of processes that began with the Big Bang, reinforcing the notion that the universe is a dynamic entity governed by the fundamental laws of physics. Understanding the beginning of the universe raises profound questions that reach far beyond the confines of science, touching on the very essence of time, causality, and existence itself. If we accept that the universe had a definitive beginning, it follows that the concept of an end is equally deserving of exploration. As we ponder the ultimate fate of the cosmos, we must confront questions that have persisted for centuries about time's nature and the limits of the universe's lifespan. Central to these inquiries are the principles of entropy, particularly the second law of thermodynamics, which guides our understanding of how energy behaves in an isolated system. Entropy, a measure of disorder, is always increasing. As the universe ages, energy spreads out and becomes less available to sustain complex processes, leading to what some describe as a heat death scenario. In this state, all energy would be uniformly dispersed, and no usable energy would remain to support life or activity. Nothing would be left to sustain the forces that drive the dynamic processes we associate with life, growth, or even movement. It is a chilling vision of the future, yet it opens up broader discussions about the nature of existence, time, and ultimate fate. Philosophically, our understanding of the universe's origins heavily influences how we view existence itself. The awareness that the cosmos may have both a beginning and an end compels reflection on the transient nature of life within this vast and ever-evolving framework. By accepting this cyclical process, we are led to reconsider the meaning and purpose of life. Are we mere blips in an infinite cosmic timeline, or do we hold a deeper significance in the grand narrative? This reflection fosters a greater appreciation for the present moment and a deeper understanding of the intricate connections that bind all forms of existence, reminding us of the fragile and fleeting nature of life. Yet, the quest to understand the universe's beginning is not solely a matter of scientific discovery. It intertwines with the timeless human pursuit of meaning, purpose, and understanding. As we explore the far reaches of cosmology, we encounter not only new data and discoveries, but also existential questions that challenge our sense of self and our place within the cosmos. The more we learn about the universe, the more we are drawn to reflect on our own existence and how it fits into this vast and dynamic system. This philosophical exploration is inextricably linked with the scientific investigation of the universe's origin and its eventual fate. Ultimately, the tension between scientific discovery and philosophical reflection shapes the way we engage with these cosmic questions. The pursuit of answers about time, existence, and the fate of all matter and energy inspires a continuous cycle of inquiry, pushing the boundaries of knowledge while inviting us to confront fundamental questions of purpose and identity. Human consciousness, in this sense, plays a pivotal role, not only in observing and interpreting the universe, but also in shaping the very questions we ask. Our capacity for self-reflection, creative thinking, and critical inquiry enables us to develop theories, refine models, and interpret data from our explorations in a way that brings us closer to understanding the forces that shape our reality. However, the limitations of human perception also play a crucial role in our understanding of the cosmos. From the early astronomers who use the naked eye to glimpse the stars, to modern physicists who rely on sophisticated telescopes and particle accelerators, human consciousness has always sought to expand the boundaries of what we can observe. Yet, these observations are always mediated by our senses and the tools we create to enhance them. As we push further into the unknown, we are constantly reminded that the way we interpret the universe is shaped by our cognitive processes, cultural backgrounds, and the prevailing scientific paradigms of the day. Scientific theories about phenomena such as black holes, the Big Bang, or dark matter are constructed through the lens of human understanding, which means they are inevitably influenced by our assumptions, biases, and limitations. Yet, even as we seek to expand our knowledge, we are simultaneously confronted by the philosophical implications of our discoveries. For example, when considering the origins of the universe, the nature of reality, or the very idea of existence, we are forced to grapple with questions that transcend the empirical and venture into the realm of meaning and purpose. It is within this intersection of science and philosophy that our understanding of the universe evolves, shaping our worldview and influencing how we relate to the cosmos. In exploring the vastness of the universe, we inevitably confront deep questions about our own existence. The anthropic principle, which suggests that the universe is finely tuned for the emergence of life, invites us to consider whether our place in the cosmos is a matter of chance or design. As we contemplate the infinite scale of the universe, we are left to wonder whether our lives, our struggles, and our triumphs have any lasting significance, or whether they are simply fleeting moments in the infinite expanse of time. Human consciousness, therefore, is not just an observer of the universe. It is an active participant in the way we interpret, question, and make meaning of the cosmos. Through our conscious engagement with the universe, we seek not only to understand the laws that govern its existence, but also to find significance in our place within it, whether through scientific inquiry, philosophical reflection, or creative exploration. We continue to search for patterns and meaning in the face of the vast and unknowable. The universe, with all its mysteries, becomes not just an object of study, but a mirror in which we seek to understand ourselves. Human consciousness has long compelled us to grapple with the ethical implications of our ever-expanding understanding of the universe. As we probe deeper into the mysteries of cosmic phenomena, we are faced with an emerging awareness of our moral obligations, not only to ourselves, but to the very planet we inhabit. With each breakthrough in our comprehension of the cosmos, the responsibility to explore knowledge with care and consideration grows ever clearer. We are no longer merely passive observers of the universe. We are active participants in a grand, unfolding narrative, intertwined with the fate of the world and the larger cosmic order. This moral dimension of our pursuit of knowledge reflects a profound shift in our awareness of our interconnectedness with the universe. It calls us to explore not just for curiosity's sake, but with the greater aim of advancing humanity and safeguarding our environment. Consciousness, that unique trait of our species, plays a crucial role in this journey. It is the lens through which we observe, interpret, and reflect on the cosmic wonders around us. It shapes our understanding of phenomena that exist far beyond our earthly concerns, but it also demands that we question our ethical responsibilities in relation to these discoveries. The interaction between our consciousness and the exploration of the universe transforms this journey into something deeply meaningful. It becomes more than a quest for knowledge. It is a reflection of our place within the vast, mysterious cosmos, a place where we must consider not only what we can learn, but also how we must act. Our relationship with the universe is not one of mere observation. It is a partnership, one that demands both wisdom and humility. At the heart of this exploration is the concept of causality, an idea fundamental to how we understand the world around us. Causality suggests that every effect has a preceding cause, that events follow one another in a predictable, linear sequence. However, when we look at the origins of the universe, particularly the moment of the Big Bang, this linear progression of cause and effect begins to unravel. The Big Bang was not merely the beginning of everything we know. It was the very birth of space and time itself. In this context, the questions of what happened before and how causality works become extraordinarily complex. Traditionally, we think of causality as a neat temporal sequence. Events unfold in a clear order, one cause leading to the next effect. But the Big Bang challenges this understanding. Before the Big Bang, there was no before in the way we experience it, because time itself emerged from this event. This raises the fundamental question: can causality, as we know it, even apply in the context of the universe's inception? If time began with the Big Bang, then the familiar cause and effect relationships may not hold. Some modern theories, especially those drawing from quantum mechanics, suggest that the birth of the universe may have defied traditional causality altogether. Quantum fluctuations, for instance, could have emerged from a vacuum state, a concept sometimes described as quantum foam. These fluctuations might have sparked the birth of the universe, not through any linear or discernible cause, but from a chaotic, uncertain quantum state. In this view, causality itself could emerge from the very uncertainties of the quantum realm, allowing for the spontaneous generation of the universe without a clear traditional cause. In this new framework, the universe may not have been created by a single, distinct event with a clear cause. Instead, it could have emerged through a series of quantum uncertainties, where the very concept of cause and effect becomes fluid. This shift challenges our most basic assumptions about reality and the universe's origin. It opens up the fascinating possibility that our understanding of causality so deeply ingrained in our perception of the world, might not apply to the birth of the cosmos itself. The more we learn, the more we realize that the universe's true nature may be far stranger and more intricate than we ever imagined. Cyclic models and multiverse theories propose alternative views on causality and the origins of the universe, inviting us to think beyond the linear frameworks that have traditionally guided our understanding of existence. In these models, the universe might experience repeated cycles of expansion and contraction, suggesting an endless loop where the universe regenerates itself, each cycle influencing the next. Alternatively, the universe we inhabit could be just one of many in a broader multiverse, with each universe interacting with one another in ways that defy our conventional view of causality. Here, events and outcomes may transcend the boundaries of individual universes, becoming interdependent and interconnected across cycles or across multiple realms, further blurring the lines of cause and effect. Such perspectives challenge our deeply ingrained assumptions about time, causality, and the nature of reality itself. They compel scientists and philosophers alike to reconsider fundamental questions about existence, pushing them to explore concepts that stretch the limits of human comprehension. As new theories emerge, our understanding of causality and its role in the origin of the universe will evolve, mirroring the complexity and scale of the cosmos. However, there are significant limits to human knowledge when it comes to understanding the universe's origin. Limits that speak not only to the constraints of our current scientific frameworks, but also to the inherent nature of the universe itself. The extreme conditions present at the dawn of the universe, such as those immediately following the Big Bang, exist at temperatures and densities where our established physical theories, particularly general relativity and quantum mechanics, struggle to offer a unified description. This intersection of physics raises profound questions about the completeness of our current models, exposing the inadequacies of our theories in explaining the circumstances of the universe's inception. The very concept of time itself, which began with the formation of the universe, presents another challenge to our understanding. Prior to the Big Bang, traditional notions of time as we know them may have simply not applied, creating a conceptual gap that is difficult to bridge. Time as a framework for defining and understanding events becomes problematic when we consider that the fabric of space and time may not have existed before the Big Bang. This creates a barrier in our ability to comprehend the universe's origins, as our most basic tool for understanding events, the passage of time, may have no bearing in this primordial state. Human cognitive limitations further complicate this issue. Our brains have evolved to process and make sense of experiences within a relatively small, manageable scale. Concepts such as infinity, the vastness of space-time, or the strange behaviors of quantum particles challenge our intuition and mental models. These ideas, while grounded in mathematical frameworks, are often beyond the grasp of our everyday understanding. This abstract nature of cosmic phenomena makes them difficult to visualize, even for trained scientists, and presents a barrier to widespread comprehension. As such, our intellectual capacities, while powerful, are not equipped to fully comprehend the magnitude of what happened at the universe's inception. Cultural and philosophical perspectives also play a crucial role in shaping how we think about the universe's origins. Our values, beliefs, and deeply held assumptions about existence, purpose, and reality can influence the way we interpret scientific data. The intersection of science and culture often leads to a blending of objective discovery and subjective worldview, meaning that interpretations of the universe's origin may differ widely depending on one's cultural or philosophical lens. As a result, discussions of origins can sometimes become entangled with values and beliefs, leading to disparate conclusions across different societies and traditions. In addition, there is the limitation of empirical observation. Much of our understanding of the early universe comes not from direct observation, but from indirect evidence. We rely on traces like cosmic microwave background radiation, gravitational waves, and other faint signals that suggest what the early universe may have been like. These inferential data are crucial, but they leave gaps in our knowledge, making it difficult to draw definitive conclusions about the universe's origins. The absence of direct observation underscores the uncertainty that still surrounds our understanding, making it clear that our current grasp of the universe's birth is far from complete. Ultimately, the challenges in understanding the origins of the universe stem from multiple sources: the limitations of our physical theories, the conceptual complexity of time, the cognitive constraints of the human mind, cultural perspectives, and the inherent limitations of observational evidence. These factors together form a profound reminder of the complexity of the universe and the vast unknowns that still lie beyond our reach. Yet, these very limitations highlight the ongoing quest for knowledge, urging us to continue our exploration and to collaborate across disciplines as we strive to deepen our understanding of the cosmos and our place within it.